Good morning, ladies and gentlemen. Welcome to the technical presentations by newly elected fellows and foreign fellows, which shall be carried out in parallel sessions. In the first group, two sub-parallel sessions featuring presentations shall be made by fellows elected in engineering sections, namely civil engineering, mechanical engineering, chemical engineering, aerospace engineering, and mining, metallurgical, and materials engineering. In the second group, two parallel sessions shall be featured for fellows elected in engineering sections, namely computer engineering and information technology, electrical engineering, electronics and communication engineering, energy engineering, interdisciplinary engineering and special engineering fields and leaderships in academia, R&D and industry. The lectures shall cover their most significant scientific and engineering contributions and highlight the motivation, novelty and significance of their work that have been recognized by their election to fellowship of the Academy. I'm sure that you will enjoy the presentations, and it shall be my delight to introduce the fellows and invite them to deliver the lectures. Starting with parallel subsession 1, it consists of three sections: engineering section 1, namely civil engineering; section 3, namely mechanical engineering; section 4, chemical engineering. We'll start with section 1, civil engineering. I invite Professor Mike John Schlack, Professor, Chair of Conceptual and Structural Design at Technische Universität Berlin, Germany, Managing Director of Schlack, Bergerman, Partner, SBP.
Dear Mr. President, dear friends and colleagues, ladies and gentlemen, please let me thank the Indian National Academy of Engineering for admitting me as a fellow. This is a great honor, and I'm looking forward to contribute to this prestigious institution. I would like to take the opportunity to quickly introduce you to my fields of activity as civil and structural engineer. My presentation is about lightweight structures such as bridges and long-span roofs, as well as solar power plants. In all these fields, we can contribute to what in German is called Baukultur, the culture of building, the art of engineering to improve quality of life. Our work must also deal with urgent issues such as sustainability. This is also addressed in the second part of the presentation, where I will quickly show you our research work at the Technische Universität Berlin, the Berlin Institute of Technology in Germany. I cannot start this presentation without mentioning my father, Jörg Schleich, who passed away just recently. Jörg Schleich was also a member of the Indian Academy of Engineering. He was a great admirer of India, and I have inherited his passion for this country and his passion for this profession. My father designed the Akka Bridge in Sikkim. You see it on this slide, India's first cable-stayed bridge back in 1988, together with many Indian colleagues. He also designed the second Hooghly Bridge in Calcutta, now called Vidyasagar Setu. At the time, it was the longest cable-stayed bridge in the world and the first with a steel concrete composite deck. My father took me with him when I was a boy to see sight in 1976. This was my first contact to India. Many years later, I had the pleasure to come back to Calcutta as independent consultant, as proof-checking engineer, to collaborate on the construction of this bridge, the second Vivekananda Bridge in Calcutta, a very impressive long-span, multi-span, extra-dose bridge. And just recently, we were given the chance to design a very long cable-stayed bridge crossing the Yamuna River, the signature bridge in New Delhi, again with numerous Indian colleagues. This is the initial design. You see the peacock feather and the cables that support a very slender, again, composite deck. And this is the final bridge, inaugurated just recently, and hopefully soon there will be a lake around it. The bridge that you see here is in Stuttgart in Germany. It can also be called a cable stayed bridge, but here the cables are flattened into steel plates, and these steel plates, like cables, but also looking a bit like sails, carry the heavy weight of rail traffic. We have worked on numerous high-speed rail bridges. Because of German unification, the country had to be stitched together again, and therefore numerous bridges like that had to be built, all concrete, integral, no joints, no bearings, so very durable, slender bridges that obstruct the view as little as possible. Here's another example of one of these integral bridges. Again, you can see that everything is monolithically connected. The deck and the piers are all one piece, no bearings, no joints. That makes these bridges very lightweight because the forces are distributed better, and durable because it's always the connections, the joints, the bearings that need to be replaced first. Another field of design activities in our office is lightweight roofs, long span and lightweight roofs. And the earliest example, again, designed by my father, is the roofs for the Olympic stadiums in Munich for the Games of 1972. Ever since then, we have worked on such lightweight roofs, and the Jawaharlal Nehru Stadium in Delhi is a nice example for that. It works a bit like a spokes wheel, a horizontally placed spokes wheel with highly tensioned cables and then cladding with membrane. This way you achieve very lightweight roofs, only 20-30 kilos per square meter, and therefore very sustainable because a minimum of resources is used. If we look inside the stadium, this is what we might see. Again, many highly tensioned cables and the membrane cladding. There's never standstill, and we are constantly trying to improve sustainability of stadium projects, that there is legacy. And here's a very nice example of a very recent stadium project for Qatar, for the Soccer World Championship next year in 2022. This stadium is completely made from containers. Containers are brought to site, materials in the containers, and it's used to build the stadium. After the event, everything can be put back into the containers and shipped elsewhere to build another stadium in another place. This is the idea. I have mentioned solar energy production already, and again, this started with my father's idea. He wrote a little booklet in 1989 with the title, "How Much Desert Does a Car Need?" Already at that time, he had thought about deserts, the solar energy from the deserts to produce energy to feed the hungry cities of the world with solar energy from the deserts. And ever since then, in our office, we have a department that works on solar thermal power plants, or PV, photovoltaic power plants. And this is also for structural engineers a very exciting field, because there is a lot of structure involved to carry mirrors or to carry PV panels. Fortunately, one of our solar thermal power plants was also built in India, the Godavari project. Here, trough collectors were used, parabolic mirrors that concentrate the sunlight on a tube, and in this tube a medium oil or molten salt is heated so much that this heat then can be used to move conventional turbines and to produce electricity. So these solar thermal power plants, again, you can see here how much structure is involved here, are an important part of our work at Schleichbergermann Partner. Let me now move to the Berlin University. We are very fortunate because we have a very big lab at our disposal, 180 meter long, so we can also build large prototypes. And here you see a stress ribbon bridge built with carbon fiber stress ribbons. Some 15 years ago, we have started to work with this very interesting material, And what you see here is a 15-meter span bridge with a 10-centimeter concrete cover, plates, and then the entire Department of Civil and Structural Engineering on it, all carried by 1 millimeter of carbon fiber bands. This is how strong this material is. There's no corrosion, there is no fatigue, and therefore we think that it is very promising for civil and structural engineering projects. At the university, we have developed cables, tension elements made of carbon fiber that can carry tremendous loads, but also they show a very interesting behavior. It's a very brittle elastic material, and when such a cable breaks, it basically decomposes in powder, black powder, as you can see here on the right side. This is a cable that was loaded until fracture. These developments, we try to transfer them into reality. And what you can see here is Germany's first network arch bridge with hangers that connect the arch to the deck, made of carbon fibers. If they would have been made of steel, due to issues of fatigue, this is a railway bridge, these hangers would have been very thick, but since there is no fatigue issues with carbon, these hangers can be very lightweight, very transparent. The bridge becomes elegant, economic at the same time, and more durable. We are also investigating the potential of pre and post tensioning concrete with carbon fibers. This is done today with steel, but again, there's the issue of corrosion. But if concrete is stressed with these very high strength carbon fibers, which are much stronger than steel, corrosion is not an issue anymore. You need less cover of concrete, and therefore these elements can become lighter than the conventional elements. You save resources, and the bridges become more elegant. The idea here is to place precast girders on abutments, cast them together so that they're integral, no joints, no bearings, and that at this way they become very efficient and durable. We have actually built one of these girders. Well, this is a fisheye photograph. In reality, naturally, this girder is straight, but it shows how slender such beams can be, all pre-stressed with carbon fibers. Now we are trying even to make the precast elements smaller, to make very small concrete components, perhaps only 1 or 2 tons of weight. Naturally, if you put them together, you have many joints, but since the stressing material to put these elements together does not corrode joints where perhaps water can get in, is not such an issue. So we're working in these areas in order to see how we can speed up production, construction, but at the same time make our bridges more durable and more elegant. We have recently discovered that with computer tomography, you can also look inside the concrete, and that is shown here. We have made samples on purpose with certain errors, 2 elements that are placed together, 2 concrete elements. You can then not only see the outside with computer tomography, but we can also look inside and see how the joints connect, and that can be very useful for future industrial production, serial production of precast elements. This is yet another example. 2 elements are stressed together in a simple way, and with and without pressure, the contact surface changes. And again, computer tomography allows us to see how much contact we really have between elements that later have to make sure that the bridge works, because these elements later bigger will then become members of a bridge. The idea of pre-stressing with carbon, we also translate it into the world of building. We do not want to build the heavy concrete slabs anymore, rather elements like that are folded slabs, very thin but very flexible. And at the left side, you see the carbon fiber textiles that come out of the concrete. So it's pre-stressed concrete, very lightweight, very slender, and very durable. These elements, you see one of them floating on a crane in our lab. was then used to build the roof of a garage, precast elements that later can also be demounted very easily. Very lightweight, 8-meter span, and only an average of 6 centimeters of concrete. This slide shows the inside of the garage on the left side. You can see again the precast elements, but it also shows a garage made out of so-called infra lightweight concrete. It's so light that it's infra, like infrared and ultraviolet. We're on one side of the spectrum. Very lightweight concrete that is very porous and that becomes insulating material. So infra lightweight concrete has load-bearing insulation. This is very important, at least in Germany, where heating energy is wasted if we don't insulate our buildings. What we use is very lightweight aggregates, inflated clay or inflated glass. And then we can build houses like that even withstand the hard German winters without additional insulation, only concrete as load-bearing insulation, as I just said, which is very good because in the end of life, this material can be easily recycled. It's not several layers of materials glued together. It's only the concrete that can then be used later again. Ladies and gentlemen, let me finish my talk with a little footbridge that shows how traditional methods and modern technologies are not mutually exclusive. They complement each other. The shape of this bridge was found with the red net that you see at the bottom, very conventional. But then the steel plates that eventually formed the bridge were cut with very modern laser technology that you can see at the top. The result is a very lightweight shell bridge that can be walked upon directly, very transparent and very stiff due to its double curvature, 30-meter length and only 20-millimeter thickness. The holes, they are not absolutely necessary, but they are very much like we've seen it on the slide before in the model. They show the flow of forces, they show the distribution of principal normal forces in the shell. So in that sense, there's some didactical quality in this bridge also. I hope I could give you a quick overview to my work. Civil and structural engineering is a wonderful profession where we can improve our quality of life. It is a vast field of possibilities, from building lightweight bridges to roofs and to solar power plants. And there's room for research with new materials and technologies to further improve our built environment. Thank you very much.
Thank you, Professor Mike. I invite Professor Vasant A. Matsagar, Dogra Chair Professor, Department of Civil Engineering, Indian Institute of Technology, Delhi.
I welcome you to the annual convention of Indian National Academy of Engineering 2021. My name is Vasant Matsagar. I am currently serving as Dogra Chair Professor in the Department of Civil Engineering, IIT Delhi. Today I will be talking a little bit about the research work we are carrying out at the Multi-Hazard Protective Structures Laboratory at IIT Delhi. My presentation will be broadly outlined as follows. I will introduce what is the current status, and then I will talk about the structural analysis and design, what are the current practices and what kind of upgradation is required in terms of analysis and design of structures when we take into account the multi-hazard effects, and how to protect our built infrastructure from some catastrophic failure that we have experienced during the past, some of these catastrophic events. Typically, civil engineers and particularly the structural engineers, we build some of the iconic structures of national importance or for the healthcare purpose or for transportation purpose. And this is called the engineered built environment or engineered built infrastructure. I need not to separately emphasize what is the importance of such kind of structures in our daily life, as well as what is their importance in terms of helping the network, in terms of our shelters that we receive, and in terms of the energy that we receive from some of the structures that the civil engineers built. In particular, some of these mega structures, their failures are quite devastating, and it might lead to some catastrophe in a particular area if at all some failure occurs. So importance of this structure cannot be overrated. However, what we have seen in the past events, particularly that in India during some of the infamous earthquakes, the non-engineered structures have experienced a lot of devastation, destruction, and there have been collapse experienced in this non-engineered built infrastructure. However, if we have a look at the engineered infrastructure as well, unfortunately, there also we have seen, especially during the Bush 2001 earthquake, that number of reinforced concrete structures, which falls in the category of engineered built infrastructures, have collapsed. Not only that, even in the other parts of the world, such as, for example, in Haiti in 2010 earthquake, one can easily see that number of structures have collapsed. They were actually engineered built infrastructures. So if we look at the past experience of how the built infrastructure has survived or how they have performed during the past earthquakes or some other similar kind of hazards, we see that there are number of failures experienced, whether it is in the building structures, towers, or whether it is in the lifeline structures such as water storage tanks, where there have been effects of the earthquake or ground shaking on the tanks in the form of formation of elephant foot buckling, diamond foot buckling because of the sloshing. There are failure at the top of the tank and so on. If we talk about the lifeline structures such as bridges, that too in some seismically developed countries such as Japan, there also we have found that during and after the earthquake, the built infrastructure, especially in terms of the lifeline structures and bridges, has experienced a number of failures, and that has hampered the rehabilitation activities which are important after any catastrophe or any hazard such as the earthquake. Even in the Indian context, also during the 2001 Bhuj earthquake, it was found that the structures have experienced failures are seen during these past earthquakes. As you can see, even in other seismically developed countries, such as that in the California region, also the bridges have experienced significant amount of damages, and some of them have actually failed. With this background, at IIT Delhi, we have focused on protecting the structures from some of the multi-hazard that the structure would experience during its service life. Now, it is argued that all these, such as wind engineering, earthquake engineering, blast engineering, fire engineering, they are independent disciplines of themselves, which requires a lot of rigorous investigation in each one of the research problems in those areas. However, our focus is on the structures. So during the service life of just one particular structure, it may experience different kinds of loading, and those loading may emanate from either wind, earthquakes, or some man-made or accidental hazards such as blast and fire. Therefore, we have focused on one structure or structural systems with some particular materials used therein exposed to different kinds of either natural hazards or man-made or accidental hazards. In addition to that, we do use some energy dissipating devices in the structures. Typically, we design these kind of systems for controlling the response of the structure against one particular hazard or one particular dynamic excitation. However, performance of the structure, which are equipped with these kind of devices under some other dynamic events or other dynamic loading, is typically not looked into, and that is one of the reasons they may not perform as anticipated during those other kinds of excitations. For example, if during the ambient condition the building is subjected to some vibration because of construction activities going around, these devices which have been put in place in the buildings or in other structures, we typically do not look into how their behavior has been. With this, we have looked into defining a research problem around this to address this need of finding out the vulnerability and the risk associated with the built infrastructure when it is subjected to different kinds of hazards. And those hazards we have quantified at a particular location, and therefore what we have investigated is the site-specific and scenario-based analysis and design of the structures subjected to different kinds of multi-hazard, and finding out if the desired factor of safety is achieved during its service life or during its design life. For that matter, we have considered some prominent hazards in our investigation, such as the earthquakes, wind, and accidental hazards, blast, and fire. It is also important to note that there are a number of new materials are being introduced for built infrastructure, and it is important to investigate their performance when they are exposed to some of these kind of events. Also, the structural systems, the build form or the shape of the structures are also being very different in nature. For example, there are some long cantilever with larger spans being built even in the seismically prone areas. So these are some aesthetical architectural requirements, and as a structural engineer, it is essential to meet some of those requirements of building the structures. If we look into the effects of these different hazards on the structures built with advanced engineered materials, we do understand that there is some interacting effect between these responses of the structure. For example, it is very well understood that in order to build the blast resistant structures, more the mass, better it is in terms of blast resistance. On contrary, if we talk about the earthquake resistance of the structures, lesser the mass, lesser is the inertial forces that it will attract. It means that there are contradictory requirements in the design of earthquake resistant structures and blast resistant structures. On similar lines, if we compare between the demand of earthquake resistant structures and wind resistant structures, typically if we elongate the time period of the structures, it means if we make them more and more flexible, then the earthquake response can be reduced down. However, flexible structures, as we know, they are more prone to the wind hazard when they are exposed to wind load. So again, there is a kind of a contradictory requirement in terms of design of earthquake resistant and wind resistant structures. Therefore, we have hypothesized on multi-hazard protection of structures that there is an interaction between these, and therefore in these events we cannot simply add them together and find out the risk. So we have to look into the individual hazards and then their interacting effects. If we see the overall worldwide, what is the status of the multi-hazard scenario, and particularly then focus on the Indian peninsula, we find that number of events take place all around the globe. In 2016, a study reported by the Engg suggests that particularly the Indian peninsula experiences number of such events, and particularly if you see the larger diameter of circles, you will find that the geophysical events such as earthquakes, tsunami, etc., that happens quite frequently and with larger intensity, especially around the ranges of Himalayas. Apart from that, there are some climatological events such as flooding, or hydrological events such as flooding, or the climatological events such as extreme temperature or drought in the Indian peninsula. Therefore, it is important to look into how the built infrastructure responds to these kind of events. So, if we see the global overview of hazards, particularly India ranks very high in terms of number of fatalities experienced because of the climatological event. Some of these striking multi-hazard events which have happened in the past tells us that we really need to design our structures to respond against the multi-hazard. For example, in 1906 San Francisco earthquake itself did not cause much of damage because in the California region structures are already built earthquake resistant. However, this earthquake triggered a fire, and that fire has almost damaged half of the city. More than 3,000 people died, and 80% of San Francisco city was destroyed during this disaster. Now, this disaster, one may say that it is because of fire, other may say that it is because of earthquake. However, it is because of the cascading effect of both these hazards, earthquake and fire. However, probably we are yet to learn the lesson, and if we see in 1994 also during the Northeast earthquake, number of such incidences were seen where earthquakes have occurred. A structure may typically, if it is designed properly, perform satisfactorily under the earthquake excitation. However, when it is subsequently subjected to some loading emanating from the fire event, then it may not have the same performance as the intact structure or undamaged structure. So that kind of philosophy is required in our design practices. All of us have experienced or seen the Fukushima Daiichi nuclear disaster in 2011. There were a series of hazardous events took place starting from earthquake and then tsunami and then fire hazard, and then there was of course the nuclear disaster. Apart from that, in 2015, I-10 bridge connecting the California and Arizona states, it has failed because of two subsequent events: heavy runs that followed the Hurricane Dolores, and because of the heavy rain there was flooding, and because of the flooding the riverbed material was washed away, causing scarring, and that led to the falling of the one of the spans in this bridge. If we look a little bit closer into these kind of problems or these kind of issues in the bridge infrastructure, what we observe is, for example, as built structure during the design stage, there is a pile cap which has been designed, and beyond that there is a pier and then pier cap. Now, the length considered for the design by the structural designer might be from the pier cap up to the pile cap up to the pier cap. Now, in this, because of the scouring that has happened in during the heavy rains, the overall length of the or free length of the structure has increased here. You can see that piles are exposed, and in the overall behavior of this column, this additional length comes into picture. Now, because of that increase in the length, the load carrying capacity reduces quite tremendously. Now, this is not one exceptional incidence where we are finding this, but there are a number of such cases that one come across where the piles are exposed to quite some extent, and overall the effective behavior of the pier changes quite dramatically. Now, during the live load condition, this may not still pose some problems, but if this is followed by earthquake down the line, then there might be some issues related to some failure of this kind of structure. So it means we need to check two independent hazard effects on the same structure, depending on what their intensities are, how they affect the performance of the structure against the different kinds of events. On similar lines, we have also investigated if a structure is subjected to earthquake excitation and otherwise if it is subjected to wind excitation, both happening at different times, not simultaneously, then how its response is affected because of these dynamic excitations and how vulnerable the structures are against those earthquake and wind loading on the structure. Apart from that, there are some other accidental events such as the blast happened in Dombivli, which was followed by fire, and here again 47 people died and more than 200 were injured. Again, this is a fire following blast kind of an event that took place in Mumbai factory during 2016. Also in 2016, same year, in the southern coast of America, in Florida, structures experienced heavy wind loading, and then there was a storm surge and followed by flood. Also, there were some events of fire, and in this multi-hazard event, more than 1650 fatalities were reported and a lot of loss because of the multi-hazard events took place. If we see the accidental hazards across the world, again we see that number of events took place which are in thousands per year in different years. If we see in terms of the cost, there are the top costliest world insurance losses because of multi-hazard, and we can see that in most cases they are not one single hazard. Top 10 costliest multi-hazard events in the world. If we focus more on the Indian context, already National Building Code of India in 2016 has included this map, which is the multi-hazard map of India, and there it is reported that mostly the northern part of India, bordering with Nepal, especially the Bihar state, it is more prone to the multi-hazard risk. It has been reported that 19% of the world's land cover is exposed to the single hazard, and more than 50% of the world's population is affected because of that single hazard. However, two hazards affect 4 million square kilometers of the land cover and more than 800 million people. And if there are more than two hazards, three or more hazards, then 0.5 million kilometers square of land cover is affected, and more than 105 million people are affected because of that. And these hazards, they have interacting or cascading effects, and thereby we need to ensure that our structures are protected from these hazards so that we can save the invaluable human life. However, I would like to highlight here that we distinguish these kind of multi-hazards into three categories. One, the independent hazards A and B, and their independent effects on one structure during the lifetime of the structure. Other is the triggering events such as the cascading hazards, and third, simultaneous occurrence of these different hazards, and obviously there will be interaction. In such cases, we need to identify what are the challenges involved in the design of the structure and how to mitigate these responses of the structure subjected to these mutually interacting and interrelated effects of the response of the structure. In that, we need to define the structural safety on some innovative scale, and in there, we require the involvement of structural designers, code writers, and other stakeholders in order to ensure that we have a multi-hazard resilient society. So here, the hypothesis that we make is the multi-hazard risk analysis are not just the sum of the single hazard or risk analysis. If we look into the other designs of structures such as the dam structures or the offshore structures, some of these conditions have been considered, though not so per se in the realm of multi-hazard protection of structures. For example, during the Oklahoma City bombing, there was a fire followed by blast. Had that building been designed using the multi-hazard concept, probably the destruction that the building has experienced might be lower, and the structure might have been usable after even these two deadliest events followed each other. So essentially, we would like to develop our structures based on all these probabilities of occurrence of this hazardous event to ensure that we lead to a multi-hazardous event. In order to do that, we carry out an assessment of the structures on the probabilistic scale to check as to how fragile they are for the different kinds of event. In that context, at IIT Delhi, in the multi-hazard protection structures laboratory, we have developed some analysis framework, analysis procedure, and some of them I will quickly highlight. For example, we have considered some multi-story mid-rise to high-rise buildings, subjected them to the site-specific earthquake scenario events and some of the wind loading events, and checked as to what are their responses, whether they are prone to failure and what are the probabilities of failure. We started with a very fundamental understanding of the single degree of freedom system response, or when it is subjected to earthquake kind of loading or wind kind of loading. I'm saying wind kind of loading because we have considered some sinusoidal excitation, that too categorized into the base excitation and mass excitation. However, while inputting these excitations, we have ensured that the total energy imparted to the structures is more or less the same. So as you can see in the time history, the total energy imparted on the structure is similar. However, response of the structure is much different. Now, if we talk about building a structure against design against the earthquake and design against the wind, it responds for similar kind of input energy is significantly different. If we see it on the stochastic scale and check the fragility of the structures, it is seen that they are more fragile to the base excitation relatively as compared to that in the wind excitation. So we have taken these intensity parameters such as the excitation frequency and figure of acceleration, as well as the mean wind speed for the exposed to the structure, and where external excitation frequencies have changed, and we found that their vulnerabilities are significantly different from one another. If we see the vulnerability on the similar scale in terms of the either top load acceleration or storage drift or top load displacement for different intensities of earthquakes and wind, we either with some energy dissipation devices or without energy dissipation devices, again we see that there is significant difference in terms of their performance. However, typically we do not design the structures in order to take care of both simultaneously, the response reduction in terms of the earthquake loading and against the wind loading. We have found that there is a bandwidth of frequencies within which these multiple hazards are affecting the structures, and the structures which are having their frequencies lying within this bandwidth are more susceptible to the different kinds of aerodynamic events. We have analyzed some industrial structures, real life industrial structures, and seen that if we provide these kind of bracing or not, the response of the structure significantly changes. In yet another real-life study, we have proposed a new analysis procedure to analyze the performance of a real-life base isolated structures built in the Aichi prefecture in Japan. So this base isolated building is about 4-story high. Base isolations are provided at the bottom. In basement floor, we have taken into account the non-linearities in the isolation system and modeled a 3D base isolated building. First of all, the data that is available for measuring the response of the building, which is being continuously monitored there. We have compared our simulation results with that, and we were able to predict the response of the structure under the action of both these events, such as the earthquakes and ambient wind. Then we have developed a framework for generating timeline of the earthquake and wind during the design life of the structure. Obviously, this is on the probability. So we developed it for first hazard, let us say for example, it's earthquake hazard, and similarly that we have repeated for second hazard, which is that because of the wind. Now here, while developing that time histories for the design life of the structure for the earthquakes and wind, because it is a random problem, there are different possibilities, and therefore we have considered some of these cases in order to simulate the wind loading on the structure and earthquake loading on the structure happening at different duration depending on what is the return period considered. So this is the designed structure as built initially. And then over a design period of, let us say, 100 years, we have subjected it to some wind events and some earthquake events in different cases and different intensities, and check how these multi-hazard events are affecting the probability of failure of the structures. And this revelation brought us to the conclusion that these isolation systems which were incorporated in the structures may not perform as they are designed, especially after a few years of their installation. So for example, here we are seeing the displacement of the structure and the against the earthquake and wind, site-specific earthquake and wind. In case of the wind, there is of course a zero non-wind oscillation, and thereby the force developed in the isolator is not comparable with that in case of the Earth. So the full development of the loop, force deformation loop, has not been possible in case of Earth. When that analysis is carried forward for a real life 25-story building, again we found some of these effects are much more pronounced. But what is most striking is within a period of about 50 to 70 years, some of the isolators have actually failed because of the fatigue loading caused due to the ambient wind. So this is an important conclusion in terms of the design, in terms of the maintenance cycle, in terms of the replacement of some of these devices when they are exposed to the multi-hazard. The other multi-hazard problem that we have solved are, for example, the fire following earthquake or fire following a blast. Very quickly, I am talking about first the post-blast fire scenario. Again, we have developed an analysis framework wherein we have analyzed these structures exposed to first the blast event and then followed by a fire event, and we have checked as to how vulnerable they are. Have the events happen independently, or if the events are happening one after the other. So this is a real life structure that we have considered. First, it is subjected to blast loading, and then it is subjected to some fire loading. This is again a scenario definition for blast and fire events. These are the nonlinear parameters considered, both dependent on temperature as well as rate of application of the load, that high strain rate parameters for the materials used in these structures. And what we found is their behavior are substantially different if only one event take place at a time, and if it is a cascading post-blast fire event. If we see the in the past that earthquake trigger fire event, there are a number of such events which have happened in the past, as I have mentioned earlier. Also in 1906, San Francisco earthquake, more than 3,000 people lost their life because of the fire, which was followed by earthquake. So we have analyzed again some real life structures that they are subjected to post-earthquake fire scenario. And what we have found is if the damaged structure is exposed to fire, the response is much more vulnerable as compared to that than undamaged structure. So we have found out the fragility or the vulnerability of the structures when they are exposed to these two different kinds of events following one another. The first is the earthquake, and then earthquake is triggering the fire. And we have found that structures become more vulnerable if they are exposed to the cascading fire, the fire event after an earthquake. Now, conventionally, these are the analysis steps that we follow for designing the structures. However, we have augmented that with the multi-hazard loading concept, with the equivalent multi-hazard load applied on the structures in order to carry out multi-hazard analysis and design of the structures. In order to carry this analysis, first of all, we need to define what are the different kinds of hazard that the structure is going to experience during its service life, and then we incorporate that in our day-to-day analysis and design of the structure. So this part of the analysis steps in the structural design of has been published in the current science journal. For details, one may have a look at those details. So we have converted this conventional structural analysis and design procedure and have added particularly the site-specific conditions and the scenario-based conditions, both on the deterministic or possibilistic to the probabilistic or stochastic. So finally, what we would like to arrive at is some multi-hazard approaches for analysis and design structures in order to have improved their multi-hazard resilience. We have been carrying out this work at the Multi-Hazard Protective Structures Laboratory at the Department of Civil Engineering, which was established in the year 2009 with this name. And there are a number of recommendations we have made based on some of these investigations that we have carried out. With this, I conclude my talk, and I will be glad to answer the questions through the chat. Thank you very much for your patient attention and interest. Have a good day.
Thank you, Professor Matsagar. I invite Professor KVL Subramaniam, Professor, Department of Civil Engineering, Indian Institute of Technology, Hyderabad.
My name is KVL Subramaniam. I'm a professor in the Civil Engineering Department at IIT Hyderabad. Today, I'll be talking about improvements in concrete processing leading to digital fabrication. This talk is about improvements in concrete technology which have led to the adoption of digital fabrication in construction. Now, this steady increase in the skyline of the buildings over the years provides the motivation for my talk. From starting from 1930s to the current day scenario, we're talking about buildings which have gotten taller. And this has been possible because of steady improvement in construction technology. In specific, concrete buildings have started taking a major share of the super tall buildings, to the point that in 2018, 63% of the super tall buildings were primarily made of concrete, with concrete structural elements and concrete structural systems. This has been possible because of a steady improvement in concrete technology, which has led to an increase in the concrete strength. Today, we are able to deliver concrete with very high strength. We are able to deliver concrete which is pumpable to great heights, steady improvement in the construction techniques, and as a material, concrete is sustainable and it is affordable compared to the alternates which are available. Now, the challenges in concrete construction today include speed. What limits the fast, rapid construction using concrete is the way the concrete is formed at site. Concrete is poured into formwork, which is assembled on site, and concrete requires vibration, mechanical intervention, to be compacted into the gaps within the formwork. The formwork is removed after concrete gains strength and concrete takes the shape of the formwork. So this entire process delays the construction of concrete structures due to the time required for assembly of the formwork. The other challenge that we face with concrete is the forming on site limits us to using rectilinear shapes. Most of the shapes that we can form on site using formwork is limited to rectangular, or where we use other shapes, it's restricted to simple shapes like I or T shapes. Now, these are not the most efficient structural elements in terms of material usage, and therefore improved forming techniques which would allow us to free form and form structures on site which are not limited to rectilinear shapes would significantly advance the use of concrete in construction. So the concrete as the construction material of the future should be more responsive to the requirement. Concrete should be tailored for delivery and placement. We have to be able to engineer the material to deliver performance during placement and ensure performance in the long run. So that is the what we expect from concrete construction in the future. Coming to concrete performance during placement, significant advances have taken place, including the improvement in pumping, the technology and the material designs which allow concrete to be pumped over great heights. Self-consolidating, self-leveling concrete, which is concrete that levels under its own weight, does not require mechanical intervention of vibration to fill the formwork, and therefore considerably speeds up the construction and reduces the requirement of labor. And finally, of course, going to formless placement, where we have form-free construction, where we are essentially talking about layer deposition and the adoption of digital manufacturing and additive manufacturing technology to construction of buildings. Now, just to illustrate the advancement in technology in pumping, concrete in Burj Khalifa, Burj Tower in Dubai, was pumped 600 meters and delivered to be placed at 600 meters. This, of course, required significant advancement in the pumping technology, the pumps that were required. In addition, the material had to be engineered to withstand the pressures so that it would flow in the pipe when it's in a highly pressurized state, come out of the nozzle, and essentially remain in an unsegregated state and fill the formwork. Similarly, if you look at superstructure of the One World Trade Center, concrete was pumped to a height of 103 meters. This, of course, then called upon the requirement of pumping technology and advances in materials that will allow us to achieve this feat. Just to illustrate what is the material level challenge in placement and forming of concrete, concrete is a suspension made of aggregate, which is in a cement paste matrix. Aggregate themselves are graded. We have coarse aggregate and fine aggregate, which pack to produce a dense matrix, and the gaps between the aggregate are filled with cement paste matrix. The cement is what provides the glue, which bonds the aggregate together when concrete is hardened and produces a structural material because of the chemical reaction that takes place between cement and water. So if you look at the flow property of concrete, we need to look at the rheology of the paste. Cement paste is the medium, the matrix in which the aggregate are suspended. So, and we have to look at aggregate packing. By engineering these two, we should be able to produce concrete with the desired flow property. To produce concrete with a self-leveling ability, require concrete to be able to flow under its own weight. The biggest challenge there is to have concrete that flows while keeping aggregate in suspension. And of course, that calls for rheology control of the binder paste and attention to packing of the aggregate. Now, coming to rheology of the cement paste, this plays a vital role in determining the flow of concrete. The rheological properties of the cement paste would be obtained if we study the shear behavior of cement paste. When cement paste is sheared, and we need to understand the flow behavior of the cement paste as to what is required to initiate flow and then to sustain the flow, the effort required to initiate flow and the effort required to sustain flow. When cement paste is sheared, it exhibits a response where initially when shear strain is applied, when we start shearing this cement paste, it offers a resistance, and the resistance offered to increasing shear strain increases up until it reaches a maximum, which is identified as yield stress. If the strain is increased beyond the yield stress, the resistance offered by the material decreases, and eventually it attains a steady state. The increase in the resistance that we get from the cement paste is because cement paste itself is a suspension of cement grains and water. The cement grains often exist in a percolated network, which is able to offer resistance to the applied shear. So initially, on applying shear stress, the percolated network densifies and it's able to offer an increasing resistance to applied shear strain. Eventually, once the applied strain exceeds a threshold value, the network is disrupted and the internal structure, the resistance offered by the internal structure is overcome, and we get flow within the cement paste. If we talk about cement paste as a suspension, this is a classical representation of a typical suspension, where because cement paste has a yield stress which comes from the internal structure within the cement paste, if we subject a cement paste to a shear rate, increasing shear rate, initially we get the resistance coming from yield stress. Under increasing shear rate, we get an increasing shear stress, which the slope of this is defined as plastic viscosity. Viscosity defines the effort required to sustain the flow in a fluid medium. And in this case, we are dealing with cement paste, which is a particulate suspension of cement grains in water. Now, viscosity and yield stress play roles in the different conditions of the concrete. So when we have an aggregate which is held in suspension of cement paste, and if the concrete is in the at-rest condition, considering the equilibrium of forces, the restoring force for the aggregate comes from the yield stress of the cement paste. The yield stress of the cement paste provides the force that keeps the aggregate in suspension when the concrete is in a static or at-rest condition. When the concrete is in flow in the dynamic condition, there the drag force which comes about from the viscosity of the cement paste comes into play in the equilibrium of the aggregate particle. Therefore, both yield stress and the viscosity become important in determining the state of the aggregate in suspension when the concrete is at rest or in the flow condition. Of course, we can manipulate the yield stress of the cement paste using these engineered polymers, which are known as high-range water reducers, which are typically engineered polymers which have a backbone and a comb teeth-like structure. And these adhere to the cement grains and essentially create a deflocculation of the cement grain structure by this physical or steric repulsion that is created between the cement grains, and we are able to induce flow. The effort required to produce flow in cement paste is reduced significantly with the addition of the water reducers. Now, coming to extrusion-based 3D concrete printing, here the ideal way, what is the representation, is to come up with a 3D representation of the structure, which is then built layer by layer. So essentially, layers are deposited on each other, and the entire structure is built as an assembly of these layers. To achieve this, one has to to achieve construction using extrusion-based layer deposition, we have to focus on the rheology of the concrete paste. We have to look at flow under pressure without segregation. Concrete has to flow under pressure, and once it comes out of the nozzle, it has to keep its shape in the at-rest condition. This mimics what we see in our toothpaste, where when the paste is pressurized, it flows out of the nozzle and it keeps its shape once it comes out of the nozzle. So this is the rheology that would have to be engineered for the concrete to achieve this layer-based deposition 3D printing of concrete. Now, extrusion-based printing of concrete would require a balance of three terms. First one is pumpability, where the concrete should have the ability to be pumped out of the pipe without clogging and segregation. This requires that the concrete itself should have low viscosity and it should not allow phase separation. The material should remain homogeneous under pressure. It should allow shape retention. Once it comes out of the nozzle, it should keep the shape with which it was extruded. That requires concrete to have a high yield stress and thixotropy. Then it should allow buildability, which means it should allow stacking of layers one on top of the other to assemble the entire structure, which means the internal structure should build up very rapidly within the material once it has been deposited. So to do this, we need to have a material with a high yield stress, low viscosity, and high thixotropy. So these are the three rheological properties that have to be balanced in the concrete. Just to illustrate that, we need a material with a high yield stress and low viscosity. The effort required to initiate flow should be high, so it will keep its shape once it has been extruded. Then it should have low viscosity so that while it's being pumped, it's able to be pumped with low effort. And then it should allow stacking of multiple layers. That means the lower layers which have already been deposited, the structure development in the layers there should allow to take the weight of additional layers that are coming on top. So CFD simulations of this print head reveals that the pressure distribution that is material, if it remains homogeneous under pressure, the kind of pressures that would develop. And if you look at the aggregate and the cement paste suspension, we can then start visualizing the pressures that the material is subjected to. In this pressurized state, we have to ensure that the liquid doesn't squirt out of the solid matrix. And as the solids are compressed under this applied pressure, the aggregate get compacted and excess paste gets squeezed out. Now, to reduce the paste from squeezing out, we have to manipulate the packing so that the excess paste content upon compaction of the aggregate in this hydrostatic compressive state does not allow the excess paste to squirt out. So there is requirement to handle aggregate packing to be able to achieve this. And once the material has been deposited, we require the material, the internal structure to build up to be able to sustain the weight of additional layers. To achieve this build-up, we have to look at the property called thixotropy. Thixotropy is once we shear the material, and if we hold the shear stress constant, then the structure breaks down. The resistance of the material breaks down because the material gets deflocculated. Then if we remove the shear stress, the internal structure within the material should build up and it should start offering resistance to shear stress. Materials which are thixotropic are able to build up very rapidly after applied stress. Now, we found that nanoclays help us improve the thixotropy of cement paste. Nanoclay, if added to cement in a small quantity, at rest, nanoclay exists in a very flocculated structure. When it is sheared, the flocculated structure breaks down, so it doesn't impact the viscosity, it flows. And once it is again brought to rest after shearing, it is able to build up the structure, which allows the material to withstand shear stress again. Just to show you uh, just to show you the viscosity recovery, this is the material when it is initially sheared at a very low strain rate. Then the material is strained at a very high strain rate, so the viscosity drops. And then after it is brought to rest, this is the viscosity that is measured when the material is again, when the high strain rate is removed from the material. And we see that with the addition of nanoclay, the structure recovers its viscosity and is able to build very rapidly. With this, by managing the thixotropy, the viscosity, and the yield stress of the concrete using water reducers, which reduces the yield stress or controls the yield stress of the material, nano and microfines, which provide packing so that we do not have segregation within the material, and clays, which provide thixotropy, we're able to engineer a concrete which offers us buildability. With this, we were able to now develop concrete mixtures with an understanding of the rheology and packing of aggregate within the concrete mixture. We were able to develop concrete mixtures which could be printed, just to demonstrate that concrete printing by layer deposition. This is an example of a structure that was printed to 1 meter height, made with aggregate which are in suspension in cement paste, or a 3D printed concrete structure with a complex shape. So with this, I would like to conclude by saying concrete for improved requirement of delivery and placement requires engineering which considers multi-scale linking between paste and concrete rheology. Rheology control of the binder paste is essential to deliver the flow behavior of concrete, or to control the flow behavior of concrete. Then multi-phase analysis, which includes packing of solids, is required to be able to engineer concrete with the desired flow characteristics. Thank you.
Thank you, Professor Subramaniam. I invite Mr. Vikram Kirloskar, Chairman and Managing Director of Kirloskar Systems Limited and Vice Chairman of Toyota Kirloskar Motor.
Good morning, ladies and gentlemen. Thank you for inviting me here. Let me start by a childhood photograph of mine with my grandfather, S.L. Kirloskar, who I admired a lot. He was a top-class engineer, also from MIT, and I learned a lot from him. And this is a photograph he gave me when I graduated from MIT. This is very, very nicely he framed it when he came for graduation. It says Vikram Kirloskar at the drawing board. And this was, I think, at Kirloskar Oil Engines, I was probably 8 years old or 9 years old. And all my life, because of my grandfather and my father died a little earlier in 84, I had the opportunity to visit the various Kirloskar factories, play around with machines, see things getting made, see metal getting molten. And that's what it was always in my mind. I must become an engineer. I always wanted to go to MIT because my grandfather went to MIT. And luckily, lo and behold, I did manage to get in, and I graduated from MIT in 1976. What were in 1981? I joined in 76 and I graduated in 81. What was most important learning from my grandfather and from MIT? I remember discussing many things in the factory with my grandfather, and he always would come down to the fundamentals of physics and build up the engineering issue out of that. And that's what we learned at MIT as well. It was fundamental science, fundamental physics, fundamental math, and how to take a large problem, bring it down to its fundamentals. And I think that was the most important thing of engineering that I learned at MIT. And that has stayed with me until now. The typical question I ask newcomers who join us, or newcomers, especially in engineering, who join us, is explain Newton's laws of motion to me. Give me examples. And that is very, very important for me. If a person can explain engineering with the fundamentals of science, I think he can do well in engineering and in his future career. So that was one item that was important to me. Second thing which I learned also at MIT was, as well as before MIT, I used to do a lot of aero modeling and various things, was how to do things with your own hands. I was fortunate to work in different labs as a lab assistant, mainly to another mentor of mine, Professor Merton Flemings. He's probably the top metallurgist in the world. He's old now, but still alive. He wrote the best known book on solidification, which is used by almost every foundry all over the world even now. And I worked in his lab, and I had the opportunity to melt aluminum, cast aluminum, process it, make thousands of tensile test specimens, and test them, and help the people doing PhDs with their results. So working with hands, working on machines always came to me. I was fortunate to have worked in a German machine tool factory as an apprentice in one of my summer holidays, and another foundry, investment casting foundry, in another holiday. So when I started work at Cummins Engine Company in Columbus, Indiana, after college, I was only there for 6 months, unfortunately. I was put in manufacturing engineering, in the manufacturing of large cylinder blocks in high volume. My first weekend, along with a friend, I said, let us walk on the middle of the transfer machine, because I have never seen this kind of a huge machine before. I've never operated it. So let's walk on the transfer bar and go across and try to understand how this thing works. And that was my introduction to really hardcore manufacturing engineering or production engineering per se, large machine tools per se. I'd always used a lathe and a milling machine, but never a large machine tool. I came back to India, joined Kirloskar Cummins as a trainee, again working in the training center, getting my hands dirty on the machine tools. But I was given a lot of challenging jobs. We started buying new CNC machines at that time in 81, 82 when I joined. And I was given the job of making them more productive, of buying them as well as making them. How do we use them? How do we make them more productive? That was my first experience of my own innovation with production engineering. Then the next very interesting thing I did, which gave me confidence, was we were replacing our cylinder head production in 82, and I designed and developed the entire line. We manufactured it as well. It was a very automated line. The number of people came down by like 80% or 90% in the new line. And it was all done with everything from India, hardly anything imported. And I think that line lasted. I left Cummins after 2 years. That line was finally dismantled after 24 years, 25 years. Some people later on told me. So this was always my experience. And right through, even while developing this kind of product, it was using fundamentals of physics, to fundamentals of control theory, whatever I had learned, of vibrations, everything, all the basic fundamentals to continue designing. But working with your hands gives you confidence, and that is what has taken me through. I worked in the machine tool business. Again, in my Kirloskar, unfortunately, it's closed just now. We redid our whole product line. We changed a lot of our products to using polymers in their bases, gluing castings together. I remember one winter in Poland at a huge tractor factory, and they wanted a big grinding machine for grinding a step of a big ring gear locating in the ring. And I sketched it for him. And the guy gave me an order. That's like the ultimate boost to your ego. We did deliver that machine. It used a lot of polymers to build it. It was huge, I think 30 tons or something in weight. And as far as I know, what I heard, it's still working. And that happened more than 20 years ago. It was fun. Later on, I got involved with the Toyota Group. Primary reason to get involved with the Toyota Group was to understand how does a large engineering company, which is the best in the world, known for its best manufacturing practices, work from the inside. What really was Toyota Production System? And we wanted to learn that as a group and implement it across our companies as well. And so we first got involved. I got involved first with the Toyotas in textile machinery, then automobiles, components, and even forklifts. We have various other joint ventures in insurance and other things, but these were the core engineering things. And we set up that plant. I set up the first plant in Biddi and the next ones. What was fun when we built the first plant, or even when we built the second plant, there was a gentleman at Toyota called Mr. Shimizu, who was the Shiramizu, who was the head of manufacturing and production worldwide. And he said, don't copy what we have. What we have is what we have done 20 years ago. So every time you build a new factory, it has to be better than the last one. If you copy something and look at something what is already there, you're going back 20 years. So this was amazing. Normally, in the past, when we've done licenses and we've learned from other people, they say, this is how we do it, you do the same. This guy says, don't do anything we are doing because it's already 20 years old. There are much better ways, use your own head. And so it was fun working with Toyota right from day one. So they would tell us the importance of process, develop the standard work, all requires top-class engineering, but use your own head, your own innovation. What you can do best, what you can do best with your skills. And we learned that. We did a lot of work in Kirloskar Group also from Toyota. I think 200-300 people I had been able to send from Kirloskar Group to various Toyota factories also through the way we were setting up our factory. We were able to start implementing what we said Kirloskar production system, improve our output to our net capital, to our gross capital assets, our gross assets. We improved 3 times in a span of 3-4 years, which means you hardly use any money in production anymore. We could improve our productivity significantly, improve our skill levels, and then the new factories we put in, new engine factory in Kolhapur, new foundry in Solapur, etc. We use these principles, and we could do much better on a global scale right from day one. So I think there was a lot of learning in all this. Again, in all this, importance of engineering is supermost. Importance of physics, importance of math, you have to have it in your mind when you start developing, whether it's a new product, a new factory, a new line, and that is important. And that is why I feel so happy. This has always been my passion, and that's why I feel so happy and so privileged to be made a member of the Engineering Academy. My little experience I've talked about. I think now my job is to keep encouraging all the newcomers who join us to maintain this spirit of science within them, as well as maintain spirit of innovation and try new ideas, new frontiers, but still maintaining the science and the engineering as a base. Thank you very much.
Thank you, Mr. Vikram. I invite Professor Atul Sharma, Professor, Department of Mechanical Engineering, Indian Institute of Technology, Bombay.
I welcome all of you to the annual lecture series for newly elected fellows. The title of this lecture is Computational Fluid Dynamics, Research, Technological and Academic Contributions. I'll start with an overview of our CFD lab. Our research interest is on theoretical and computational continuum mechanics involving both solid and fluid mechanics. The specific interest is on fluid structure interactions involving fish-like locomotion and FSI-based energy harvesting. Two-phase flow involving droplet coalescence, droplet collision, and droplet combustion, and nucleate boiling under zero gravity and transient conditions. Recently, we have also started working on biofluid mechanics, where we are developing our in-house codes for flow solver, structural solver, and acoustic solver, as well as using machine learning techniques for sound-based detection of blockage in the artery. The vision of the lab is to develop unified computational methodology for coupled fluid and structural dynamics and its application for analysis of wide range of scientific and industrial problems. The mission of our lab is innovate, discover, and make open source physics-based simulation software in India. Our research contributions is that we have developed a range of novel and efficient computational tools, demonstrated its application to a large number of time-consuming simulations, and presented analysis of the resulting big data for a wide variety of problems in CFD. Technical contribution is that we have demonstrated simulation of arc formation inside circuit breaker, radiator fan assembly of power transformer, pebble-based reactor, and printed circuit heat exchanger. Academically, I have proposed a physical, insightful, and comprehensive approach to make the subject of CFD easy enough to be taught at an early undergraduate curriculum that can enable make physics-based simulation software in India. The focus of this presentation is whatever is marked in red, where I will discuss the fish-like locomotion for the research contribution, radiator fan assembly of power transfer for the technical logical contribution, and the proposition of the physical, insightful, and comprehensive approach for CFD in an academic contribution. The title of the research contribution is Biomimetic CFD Study on Fish-like Locomotion of a Hydrofoil, Effect of Unified Kinematics, Hybrid Kinematics, and Continuous versus Burst and Coast Swimming. In nature, it has been found that 80% of the fishes are of certain types called as body and caudal fin fishes. So for such type of fishes, they are further classified into 4 types called as anguilliform, subcarangiform, carangiform, and cuneiform, where the for angular fishes, the body motion is as shown here. They do what they call as the undulations. The cuneiform fishes, the front part of the body is almost stationary, and they have a tail. And the cross section of this tail, if you take the lateral cross section, it is hydrofoil shaped, and the motion of the tail is in the transverse direction. It is this what is called as a pitching motion. So this is the undulating motion. This is undulating motion of the anguilliform fish body, and this is the tail motion corresponding to the cuneiform fishes. And the subcarangiform and carangiform fishes have body undulation, which is a combination of the undulation as well as pitching. So we have come up with a unified kinematics where the mean chord transverse undulations, which is represented as delta y as a function of time. So we have come up with a kinematical equation where for various values of lambda, you can get this undulations and pitching motions as well as its linear as well as combinations. So you can see this delta y as it's not only function of time, it's function of the this is like undulating wavelength, and there is an amplitude of the traveling wave which is also a function of the streamwise direction. So there are 2 parameters for the kinematics. One is the undulating wavelength, and the second is the amplitude. And using this equation, we have shown that for lambda is equals to 1, you get an undulating kinematics corresponding to anguilliform fishes. And as lambda approaches towards infinity, you get a pitching motion corresponding to the tail of the cuneiform fishes. So we have done a 2D study considering this 2D hydrofoil and presented a unified kinematic study. For this problem, when we study the propulsive characteristics as well as performance, there are certain forces which are important. The fish body, when it does the swimming, it generates a force which is called as thrust force, which propels it in the forward direction. There is another force which acts, which is in the lateral direction. This is called as the lateral force. In nature, it has been found that the body of the anguilliform fishes at certain times, as per its need, adapts the amplitude of a body of a carangiform fish. Note that from here that the amplitude of the body increases from anguilliform to the carangiform fishes. So due to as per the need, the anguilliform fishes adapt the larger wavelength of the carangiform fish so that they can increase the thrust. So we are motivated by this natural observation, and we have done a detailed study that will present for the adaptation of wavelength and or amplitude envelope. In nature, it has been also found that the carangiform fishes, which is this type of fish, thicker fish, they do at certain times when they have to travel a long distance, they want to save their energy, and they do a swimming which is different from this continuous swimming. So this is called as burst and course swimming. So in this case, they undulate their body for 1 cycle, then they rest for 1 cycle, then they again undulate for 1 cycle. So they have an alternate acceleration and deceleration of the during the burst and course swimming. And it has been found in nature that this leads to energy saving to travel a long distance, although it leads to an increase in the travel time. So I'll present here the results for the unified kinematics, hybrid kinematics, and continuous versus burst and course swimming. For the unified undulation pitching kinematics, this is the variation of the thrust force coefficient. So as I mentioned that the lower lambda corresponds to the anguilliform undulations and the larger lambda corresponds to the pitching. So you can see that with increasing lambda, there is an increase in the thrust force coefficient. So which means that the pitching motion leads to a larger thrust coefficient. This figure also shows that the thrust coefficient increases with the increase in the frequency of undulation. This Strawell number is a non-dimensional frequency of undulation. So you can see from this figure that the pitching motion corresponding to the carangiform tail of the carangiform fish leads to a larger thrust coefficient. But when you compare the propulsive efficiency, although the pitching motion leads to a larger thrust force coefficient, but it leads to a smaller efficiency as compared to the lower lambda of the undulating motion of the anguilliform fishes. We have also compared the flow patterns corresponding to the low lambda undulating motion and the larger lambda corresponding to the pitching motion. where the larger thrust coefficient corresponds to the stronger vortex generations. And we have also compared the pressure distributions through this temporal variation of pressure distribution, as well as the temporal variation of the thrust coefficient and the lateral force coefficients. So in CFD, we generate this type of movies where in this movie, the actor is the velocity and the vorticity. Here, the actor is like a pressure. And the character of this fluid dynamic movies are the fluid dynamic phenomena like boundary layer, flow separation, vortex formation. And we try to correlate this scientifically exciting movie with this engineering relevant movie to make up a story which is scientifically as well as engineering relevance. So for the hybrid kinematics, I have mentioned that it has been found in nature that carangiform fishes, when it does its body undulation, it uses the lambda is equals to 1. Anguilliform fishes, normally it uses lambda is equals to 0.6. But as per the need, when it has to increase the speed, it has been found that the anguilliform fishes increases its lambda from 0.65 to 1. So here we are doing a study on adaptation of the lambda and amplitude envelope separately as well as together. So since anguilliform fish is a thinner fish, whereas carangiform fish are thicker fish, we have taken the data from the literature where experimentally people have documented the ratio of the thickness and the length, and we have mapped those fineness ratio with the appropriate various types of thin NACA hydrofoil and thick NACA hydrofoil, which is as shown here. So these are the thin NACA hydrofoil corresponding to this anguilliform fishes. These are the thicker hydrofoil corresponding to carangiform fishes. And we have considered the adaptation of, so this is the anguilliform fishes using the lambda is equals to 0.65 and this amplitude envelope. When you consider ACA, this means that anguilliform fishes is using a larger lambda. And when you have AAC, in this case, it is using the envelope of the carangiform fishes. And in this case, it is using the amplitude as well as the wavelength of the carangiform fishes. Similarly, we have considered the adaptation of carangiform fishes. This is the carangiforms under natural condition. This is with the adaptation of the lambda of anguilliform. This is with the adaptation of amplitude envelope of the anguilliform, and this is the adaptation of both lambda and amplitude. So for the adaptation of lambda, we have considered the various 3 different types of NACA hydrofoil for anguilliform and 3 different types of hydrofoil for the carangiform fishes, thinner and thicker ones. And we have seen that here the solid line represents under natural condition and the dashed line is corresponding to the adaptation. So here you can see this is the thrust coefficient. So with the adaptation for the anguilliform fishes, thrust force coefficient increases, whereas for the carangiform fishes, the thrust force coefficient decreases. Note that in nature it is seen only by the anguilliform fishes. So our results confirms the increase in the thrust force coefficient that leads to the increase in the speed for the anguilliform fishes. However, when you vary the amplitude, so we have considered along with lambda the variation of amplitude envelope also, adaptation of amplitude. When both the type of fishes adapt the amplitude of the other fish, it is seen that there is almost no change in the thrust coefficient. So when you consider the adaptation of both, this result is very similar to the adaptation of only lambda star. So this was about the thrust force coefficient, but if you consider the efficiencies, so although the anguilliform fishes has a larger thrust coefficient, but you can see that it leads to when it adapts the lambda of the carangiform fishes, there is a decrease in the propulsive efficiency. So the adaptation for the anguilliform fish leads to an increased thrust. So momentarily it can get a larger speed, but there will be a increase in the efficiency, so it has to spend more power. So here I'll present the fish-like locomotion of a hydrofoil continuous swimming. So when the undulation of the hydrofoil starts, it initially does an acceleration and then finally it asymptotes to almost constant velocity, which is as shown here. This is the temporal variation of the propulsion velocity. So initially there is an acceleration and then it reaches almost to a constant velocity. We've also plotted the variation of the velocity vectors and the vorticity contour. This is a case corresponding to lambda is equals to 0.8, so which is corresponding to the undulating hydrofoil. And this is the fluid dynamic movie for the velocity vectors and the vorticity contour for a pitching motion of a. So you can see that pitching motion leads to a stronger vortices and it leads to a larger propulsive velocity. So the carangiform fishes have much larger velocity as compared to the angliform fishes. In nature, it has been found that there are carangiform fishes do another type of swimming that is called as burst and coast swimming. So in a continuous swimming, this is the propulsion velocity, but along with that, here I am showing you the input power coefficient. So to do this undulation, it has to spend certain power. So this is the variation of power coefficient. So you can see that with time, the power, not only the thrust coefficient, but the power coefficient, there is an asymptotic increase. This is the increase in the propulsion velocity and the increase in the input power coefficient. However, if you can see that as lambda increases, there is increase in the propulsion velocity as well as the input power coefficient. So in our simulation for the burst and coast swimming, we have found that both propulsion velocity, so when it undulates for one cycle and rest for one cycle, there is increase in the velocity with which it is moving, but there is also a decrease in the input power coefficient. However, we have found that there is a much larger decrease in the input power coefficient as compared to the decrease in the propulsion velocity by doing the burst and coast swimming, such as for the lambda is equals to infinity, we have found that there is a decrease, 60% decrease in the power coefficient as compared to 30% decrease in the propulsion velocity. So when the burst and coast swimming is adopted by the carangiform fishes, it's saves substantial energy, although there is increase in the travel time due to the decrease in the propulsion velocity. So although but 2D simulation had a lot of limitations, but we have demonstrated the natural observations through our simplified cases of simulations. Moreover, we considered a more realistic 3D simulation for a fish which is like a bat, which is as shown here. So it has a wing which goes up and down. So we have considered an ellipsoid model corresponding to this. So we have considered the top view of this fish as an ellipsoid. The frontal cross section is like an hydrofoil, and if you consider the streamwise cross section, it is like a plate which is doing a flapping motion. And the kinematics we have modeled as shown here. So you can see that the various frontal cross section are hydrofoil which are doing undulating motions. If you consider a streamwise cross section, then it is shown as like a flapping motion. For this 3D simulations, we've also plotted the vorticity patterns and also obtained the variation of the thrust coefficient for varying lambda. The title of the technological contribution is CFD study on radiator fan assembly of a power transformer. This is a solid model for the radiator fan assembly, where this is the radiator where oil is flowing from top to bottom. And in this case, the airflow by the fan is from bottom to top. In this case, this is a horizontal blowing fan. So this airflow is from left to right. This is a fluid dynamic movie corresponding to the variation of the resultant velocity contour across the various cross section of the vertical blowing. This is the vertical blowing fan and this is the horizontal blowing fan. We have found that the horizontal as compared to vertical blowing fan is more efficient in dissipating heat from the radiator assembly as less air gets wasted from the sides. So we have demonstrated that horizontal fan flow is better than the traditionally used vertical fan flow. The title of the academic contribution is Physical Law and Discrete Math Based CFD. So in fluid mechanics, we start with the conservation law and apply it to a control volume. Then we use limit delta x, delta y, delta t tends to 0, and finally obtain a governing differential equation. And if you see all the books in CFD, they start with this governing partial differential equation, and they apply the Gauss divergence theorem and use continuous maths based approximation to come up with a derived and linear algebraic equations, which are the governing equation in CFD. So I have authored a book in which I have proposed a physical law instead of partial differential equation and discrete independent of continuous math based finite volume method, where I have presented that we can derive the same algebraic equation from the conservation law, where we use a discrete form of the conservation law and we use a discrete math to obtain the same set of linear algebraic equations. So with this, I have tried to make this subject more of physics, less of math, so that it is easy enough to be taught at an early undergraduate curriculum to enable make CFD software in India. Finally, I would like to thank all of you for your attention, and I would like to acknowledge my gurus, Professor J. Srinivasan, Professor Ishwaran, Professor Muralidhar, my institute, my colleagues, Professor Amit Agrawal, Professor Suhas Joshi, and my students, especially at CFD Lab. And I would also like to acknowledge my funding agencies and collaborators. Thank you for your attention.
Thank you, Professor Sharma. I invite Dr. B.K. Sridhar, Scientific Officer H, IGCAR, Kalapakkam.
So I am Dr. B.K. Sridhar from the Indira Gandhi Center for Atomic Research. The topic of my lecture is development and testing of components for fast reactors. So in this brief lecture, I'll be giving a glimpse of the activities that I have personally been involved in and that conducted by my team of engineers related to the development and testing of components for the prototype fast breeder reactor. Now, the prototype fast breeder reactor, PFBR, is a pool type liquid sodium cooled reactor. So there is a primary loop in which liquid sodium is circulated. And then there is a secondary loop where again liquid sodium is the coolant, and a tertiary steam water circuit, which is a conventional steam water circuit. So in the primary loop, centrifugal pumps are used to circulate sodium through the reactor core. The heat extracted by the primary sodium is transferred to the secondary sodium in the intermediate heat exchangers. So sodium is circulated in the secondary loop by centrifugal pumps again, and the heat in the secondary loop is transferred to the steam water circuit in the steam generators, where steam is produced to run turbo generators and produce power. Now, this is a sketch of the primary pump in the cold pool of the reactor. So the primary pump is located in the cold pool, which is inside a main vessel. The cold pool is at a temperature of 397 degrees centigrade. Now, the centrifugal sodium pumps used in fast reactors have a lot of unique characteristics, such as it's designed to operate at an inclination from the vertical because it has to accommodate thermal expansion. And then it is supported in sodium by hydrostatic bearings. And it has to operate over a range of speeds from 20% to 100% of the rated speed, and so on. Now, development work was taken up in the late 80s and early 90s, primarily because of the prevailing embargo, which prevented the sale of equipments and fast reactor technology to India. Now, the sodium pumps are quite different from heavy water pumps. And in fact, heavy water pumps, that is the pumps used in PHWR reactors, have got the benefit of having Indian subsidiaries of international companies from where they can purchase the pumps. But since, because of the embargo, we were forced to carry out the development work on our own. Now, the pumps operate in a limited NPSH environment, which means that we have to do detailed cavitation testing. Moreover, the pumps have to be made as compact as possible because the pumps are located in the main vessel and they directly influence the size of the main vessel. So these are two conflicting requirements for which detailed cavitation testing has to be carried out. Now, I was personally involved in the hydraulic development of the pumps, which was carried out through detailed model studies in water. The work was done in association with Messrs. Kirloskar Brothers Limited, Pune. Now, the work has been successfully completed. The pumps have been manufactured, tested in water, and they are under commissioning in the reactor. Now, since then, I have developed a cavitation test facility to understand and compare the cavitation resistance of different materials in sodium. And we have also embarked on a program to develop oilless bearings and seals for pumps. Now, this is this slide actually shows the visual cavitation tests that we did on the model pumps. The model pumps were provided with Perspex windows on the intake skirt and Perspex front shroud to facilitate the observation of cavity growth with reduction in passage. So the cavity was observed under stroboscopic lighting and measured using a prefixed grid on the impeller. And the size of the cavity was used to estimate the impeller life based on empirical test results. We also carried out detailed erosion testing on the impeller, and these are the results of the paint erosion test. A special paint was developed for this purpose, and this test allowed us to compare different impeller diffuser combinations for their erosion damage resistance, as well as to compare the effect of intake skirt arrangement on the cavitation performance of the pump. We also carried out buffed specimen erosion tests, wherein we spot welded stainless steel buffed specimens on the areas identified by the paint erosion test, and carried out long-term erosion testing to determine the weight loss resulting from cavitation. This is a facility which I developed in order to understand and compare the cavitation damage resistance of different materials in liquid sodium. Now, as mentioned earlier, by improving the design of the pump, the design of the impeller, diffuser, and the intake skirt combination, we can increase the suction specific speed of the pump. And a supporting technique will be, a method will be to use cavitation resistant materials or consider surface treatment or hard facing in areas which are prone to cavitation damage. So this cavitation test facility helps us to do the damage resistance comparison of different materials in a very simple manner. Now here basically ultrasonic vibration is used to generate cavitation in sodium. The advantages are the testing is very rapid and the method is standardized, which means that the comparison of materials is more foolproof. Now, this slide shows the results of a test carried out in sodium at 250 degrees centigrade on a stainless steel specimen. As it can be seen, the damage is quite intense. In a few minutes, we are able to produce measurable weight loss, and in about 1.5 hours, the surface is severely pitted. And the resistance capability of different materials is quantified in terms of weight loss rate. And these graphs show the comparison of 316L, stainless steel 316L, with colmonoid coating and stellite coating. So we have also started a parallel program on the development of oilless bearings and seals. Now, as I said earlier, the pump rotor is supported inside sodium by means of a hydrostatic bearing, but outside the argon cover gas, it is supported by oil-cooled bearings and mechanical seals. Now, although there are engineered design features to prevent the ingress of oil into sodium, there have been instances elsewhere of oil leak into sodium. This can lead to extended shutdown of the reactor. So one way is to eliminate oil completely, and a suitable candidate is the active magnetic bearing. Now, the active magnetic bearing was developed with NAL Bangalore, CSIR NAL Bangalore, and we integrated the bearing with a small sodium pump that we have in our facility. The pump was then run in a water loop over a range of speeds from 600 to 2900 RPM. These are the results of the tests, and the bearing operated very well. Now, as mentioned earlier, the primary pump in the reactor has to operate with an angle of inclination to the vertical because of the relative thermal expansion between the cold and the hot pool. So we did rotordynamic studies on a scaled model and to understand the effect of inclination on the lifting capacity of the bearing. And these tests have also been successfully completed. And in tandem with the development of magnetic bearings, we have also started a program on development of ferrofluid seals, because only then can the pump be truly oil-free. Now, the ferrofluid for this purpose was developed in-house by the Metallurgy and Materials program, and we have been involved in the design and testing of the seals. We are basically interested in finding out the influence of parameters such as the surface speed, the clearance, seal clearance, the effect of temperature, the effect of sodium aerosol deposition, and the volatility of the ferrofluid vis-a-vis long-term operation. So far we have been able to achieve a burst pressure of about 350 millibars in the static condition, and the system has operated well at about 100, close to 90 millibars at 1000 RPM for a period of 3.5 months. Of course, this is a work in progress, and we have understood and solved some problems, and we are continuing with it. Now, in addition to these development works, my team and myself, we have been engaged in the designing facilities as well as testing full-scale components for PFBR. The thermal shock test facility is a unique facility which was designed and commissioned by us to study the effect of thermal shock produced from thermal transients. In the nuclear reactor, in the case of a SCRAM, the electromagnet of the shutdown system is subjected to a severe thermal shock where the temperature drops from 500 to 400 degrees centigrade in a few seconds. So we have been able to simulate that, and this facility has been in operation for almost 15,000 hours at well above 500 degrees centigrade. Now this slide shows you the performance testing that we did on the prototype inclined fuel transfer mission, which is the X-vessel fuel handling mission in the prototype fast breeder reactor. Now here, this mission is used to transfer the spent subassembly from the pool to the outside where it will be taken up for reprocessing. Now we tested the full-scale mission in our test facility, simulating the operating conditions, namely operation at 200 degrees centigrade, and then the system is parked at 500 degrees centigrade when the reactor is in operation before it is brought back once again for refueling at 200 degrees centigrade. So this was successfully completed by my team. This is another fuel handling machine, namely the transfer arm, which is the in-vessel fuel handling machine. While here the inclined fuel transfer machine removes the subassembly from the pool to the outside, the transfer arm takes the fuel subassembly from the core after the desired burnup is achieved and moves it to the in-vessel storage position for cooling. So this machine is about 24 tons in weight and weighs about 25 meters in height. And we have successfully tested the machine, simulating all the operating conditions in the reactor. Some of the challenges or the major challenges we faced while testing these prototype components was that most of these components are slender and heavy, and they operate with very close tolerances. So we had to be involved in a lot of troubleshooting, which was a real experience. Finally, after we test all these components, we have to remove the sodium adhering onto the components before it is taken up for inspection and disassembly. This is because the sodium is liquid sodium is pyrophoric, and so before we before we bring the components outside, we have to remove the sodium. So this is done using a specialized process, namely the water vapor carbon dioxide process. This process has to be done carefully because there is hydrogen evolution when the reaction is in progress. While while doing it at the lab scale is easy, it's quite a challenge to do it for the full scale components. But my team has successfully completed this, and in fact, we have tested a number of prototype components, namely the fuel handling machines, the centrifugal pumps, the under-sodium scanner, and the shutdown mechanisms, to name a few. So in conclusion, this presentation gives you a glimpse of the various activities that me and my team have been involved in towards development and performance testing of components of PFBR. Thank you very much.
Thank you, Dr. Sridhar. I invite Dr. Satya Prasad Mangalaramanan, Vice President, Product Development, Ashok Leyland Limited, Chennai.
Namaste. I am delighted to deliver this presentation to my illustrious INAE colleagues. First and foremost, my most sincere thanks to INAE for electing me as a fellow for the year 2021. It is a singular honor. My journey after my undergraduate has taken me through exciting experiences that started as a marketing and application engineer in Larsen & Toubro, followed by 5.5 years as a master's and doctoral research student. Subsequently, I worked for Babcock & Wilcox Canada as a design engineer in nuclear engineering. Thereafter, I spent almost 5 years in the USA with Dana Corporation before coming back to India in 2004 to serve my country. Observing and questioning has been the basis of my research. Some of the questions that drive me are: what is our relationship with Mother Nature? Is it good to approximate in engineering? What is the potential of Swadeshi technologies? What could India bring to globalization? And could an engineer dabble into literature? Let me give some examples. We are all familiar with armored vehicles. Nature already has the concept of exoskeleton. The roll cage in a race car perhaps took inspiration from the endoskeleton in mammals. The jellyfish does not have a skeleton, and likewise our parachute. We created money with the brains that nature has given us. Let me explain this further. The safety factor of a cantilever beam shown here is localized on the left extreme, the red patch. If we think a little and move materials slightly around, the safety factor assumes a whole new purpose. The entire structure uniformly bears the load. In other words, the factor of safety is not localized anymore. Nature has been doing it for millions of years. The tree branch you see has already introduced us the concept of minimum weight or shape optimization. Nature is never accurate, but always usefully approximate. I was intrigued by the bow in this Jarva's hands. Who taught him to design a bow that progressively tapered towards the ends? Perhaps experience passed on from generations. Yet, such a design is not only lighter, but is also capable of storing more energy, thus shooting arrows to longer distances with every twang. Suddenly we realize that the shape of the Jarva's bow is no different from the tusks of an elephant or the horns of a bison. Nature has again scored over us. Now we could relate that even our modern automobile leaf spring has much in common with the Jarva's bow. I was intrigued if it would be possible to mimic nature. Our preconceived design concepts are Euclidean. Nature is hardly so. Is it possible to let a structure decide for itself on the shape best suited to serve the purpose? This research made me develop ground-up structural shape optimization theories, leading to code a software I call Robin Hood and its more powerful version, Stingineer. Stingineer stands for Stingy Engineer, which is a fundamental ethos for an engineer. Conserve resources. I have made Stingineer available for free. I was, to a significant extent, able to mimic nature. I took a Euclidean baseline structure as you see here and optimized it with Stingineer. What came out had an uncanny resemblance to the branch of a tree. Stingineer was applied to several engineering components with huge success. What you see here is the subframe of a Class 8 truck. In its previous version, Robin Hood, it was a runner-up for the prestigious PACE Award in the USA. Optimization does not mean the elimination of redundancies. It only underscores a much better understanding of the relevance of a structure. Here again, nature scores over us. While nature has given us 2 eyes, 2 ears, 2 kidneys, etc., it has been clever in giving us only 1 stomach, 1 heart, and more importantly, only 1 brain. Imagine how confused we would be if ever we were provided with 2 brains. Nature knows where redundancy is essential and has no plans for a value engineering exercise. It has been doing its job for millions of years and hence has evolved beyond our imagination. Sometimes we tend to take comfort that structural redundancy is a measure of safety. We automatically are biased to think that redundancy is some kind of insurance against failure. as in the case of the truss structure on the right, which has 3 members as against the minimum requirement of 2. But simple analysis shows that more is not merrier. The structure on the left is a stingy structure. The structure to the right has extra material, in other words, redundancy. This does not make the structure to the right automatically stronger than the structure to the left. If you look at member number 2, in both these cases, what we would have thought of as a stronger structure, that is on the right side, has 20% weakness when it comes to buckling. I have spent several years trying to qualify structural redundancy and move designs towards what ASME boiler and pressure vessel code calls the primary stress. Redundancy must have a purpose, and that is what nature is teaching us. Another engineering domain that continues to fascinate me is approximation. More than 2 millennia ago, Aristotle understood the importance of approximation when he said, "It is the mark of an educated mind to rest satisfied with the degree of precision which the nature of the subject admits, and not to seek exactness where only an approximation is possible." My mantra in engineering is, don't miss a chance to approximate. Don't chase non-value added and expensive accuracy. Leave precision to scientists. We are engineers. Be practical. The pursuit of approximation led me to develop simplified methods in estimating limit loads and reference volume. The volume of a structure that gets involved in, say, an event such as an impact is called the reference volume. Some of my approximate methods were applied to the interesting problem of nuclear tube sheet design. To give you some idea, these components are more than a foot thick and almost 12 to 14 feet in diameter. Around 5 to 6,000 accurate holes are gun drilled, making the whole process cumbersome, demanding, and expensive. Even a small reduction in plate thickness would offer significant cost savings. My methods showed the potential for huge cost savings. In the commercial vehicle transportation sector, I have focused the earlier part of my career on pedestrian safety during impact with the front of the bus. The learnings were exciting and useful. I had the good fortune of collaborating with IIT Delhi on a joint activity called Pedestrian Safety Consortium of India, PESCI. Such collaborations between academia and industry are required to take our country forward. I was responsible for launching India's first single tire and dual tire lift axles in the heavy commercial trucks in our country. These products have been extremely successful. All these activities have culminated into 18 patents, 16 journal and 31 conference publications. From the standpoint of my non-engineering contributions, I have made in-depth and original research on the effect of globalization and free market on countries like India. The video is available on the YouTube. Whenever I get some time, I write articles which I publish on my website. I have also self-published a book on the basics of Advaita philosophy. Looking back, I cherish my intellectual pursuits. I herald an even more exciting future. There are lots of emerging areas like deep learning, artificial intelligence, data analytics, quantum computing, and so on. I think virtual reality and augmented reality would be playing a significant role in the future. So, as Frost puts it, I have miles to go before I sleep. And so, let me conclude by quoting the Rig Veda. Ano Bhadra Kritavo Yentu Vishwataha. Let noble thoughts come to us from every side. Thank you very much for this wonderful opportunity. Wish you all the very best.
Thank you, Dr. Prasad. I invite Professor Arup K. Chakraborty, Robert T. Helsom Professor of Chemical Engineering, Professor of Physics, Professor of Chemistry, Massachusetts Institute of Technology.
For over 2 decades, my work has focused on trying to understand how the immune system functions and then trying to harness that knowledge toward practical ends. The human story cannot be told without also recounting the suffering caused by infectious diseases. COVID-19 is a recent reminder. SARS-CoV-2, the virus that causes the COVID-19 disease, is an example of viruses that have especially wreaked havoc, particularly since our ancestors learned how to grow crops. When this happened, they started living in large communities so they could transmit viruses to many others. And they also started to domesticate animals, and so the pool of viruses that used to circulate in animals began to circulate in humans. The reason we are still around as a species is because we have an adaptive immune system, which is remarkable in that it enables us to mount pathogen-specific responses against a diverse and evolving world of microbes. Isn't it amazing that a person infected by SARS-CoV-2 today can mount a bespoke, tailored immune response to this virus, which evolved after this person was born? To roughly see how this works, consider infection with a virus. When a virus infects a host cell, it hijacks its transcriptional machinery, enabling the synthesis of many viral proteins and the assembly of many virus particles that can go on to infect other cells. B cells are important players in adaptive immunity. We have about 100 billion B cells, and most B cells have a receptor on the surface which is distinct from the receptor on the surface of another B cell. If the receptor on this particular B cell can bind sufficiently strongly to the spike proteins of this particular virus, then biochemical reactions cause it to get activated, it starts to proliferate, and a Darwinian evolutionary process occurs, which I shall describe a bit later, which ultimately leads to secretion of soluble and even higher affinity forms of this receptor, and that's what we call an antibody. These antibodies can then bind specifically and strongly to the spikes of this particular virus and then dispose of it in a number of different ways. But antibodies attack virus particles that are free in blood or extracellular spaces. Now, some of these viral proteins are chopped up into short peptides, about 10 amino acids long, and are displayed on the surface of human cells in complex with human proteins called HLA proteins. We each have 6 to 12 types of these HLA proteins, but there are thousands of variants in the human population. And different HLAs tend to bind different peptides. T cells are also important players in adaptive immunity. We have about 100 billion T cells, and most T cells have a distinct receptor on their surface. If the receptor on this particular T cell can bind sufficiently strongly to this particular viral peptide, it gets activated, it begins to proliferate, and then it can coordinate an immune response in a number of different ways. For example, certain kinds of T cells called CTLs are such that if an activated CTL sees another cell displaying the same peptide that originally activated it, then it can secrete products that will kill this infected cell and the virus particles that it harbors. Now, after you have cleared an infection, most of the B cells and T cells that proliferated in response to this particular infection die, but a few remain as so-called memory cells that can then mount robust and rapid responses upon reinfection with the same pathogen. This pathogen-specific immunological memory is the basis for vaccination. With a vaccine, you try to induce memory B cells, T cells, and antibodies that are specific for the bug against which you wish to protect the host. Now, as you can see, these processes are cooperative, stochastic, dynamic events with many participating components that span scales and must act collectively in order for an immune response to develop. Therefore, it is often difficult to intuit underlying mechanisms by looking at observations alone. Over the past 2 decades, we've tried to help confront this challenge by bringing together theoretical and computational approaches rooted in physics and engineering with a diversity of different biological experiments and clinical data. The experiments and the clinical work have been done in collaboration with collaborators who are immunologists all over the world. Now, I'll give you some snippets of my work today that is focused on vaccination, which has saved more lives than any other medical procedure. Indeed, one important reason we see a light at the end of the tunnel of this pandemic are effective vaccines. But we do not have effective vaccines against highly mutable pathogens. HIV is a prominent example. We do not have effective vaccines against different mutant strains of influenza that emerge every year. So we have to take a different shot every year. SARS-CoV-2 does not mutate as rapidly as influenza, but if global vaccination efforts are successful, then there will be enormous selection pressure on this virus to evolve mutations that will evade these immune pressures, the vaccine-induced immune pressures. What is required to eliminate these scourges are universal or variant-proof vaccines, and I'll give you, in the remaining time, just snippets of some of our work which represent small steps in pursuit of this quest. Now, a major barrier to the quest for a vaccine against HIV is the high mutability of the virus. In these phylogenetic trees, the number of Ns corresponds to the diversity of circulating strains. As you can see, the diversity of the flu virus in the entire world is comparable to the diversity of HIV strains in a single infected individual and completely dwarfed by the diversity of strains in just one region in the world, city in the world, and completely dwarfed by the diversity of strains in just one region in Africa. This high diversity, mutability, presents a challenge to vaccination because HIV can mutate to evade vaccine-induced antibodies and T cells that lie ready and waiting for certain specific types of strains. So I'm going to briefly tell you about some of our work on the T cell arm of this challenge in the context of HIV, and then briefly touch upon some of our work on the antibody arm of this challenge in the context of influenza and more generally. The T cell work has been going on for a while and has involved many junior students and postdocs who have gone on to independent careers or are even more gainfully employed, and has also involved collaborations with a number of senior scientists. So what we did here is the following. Over the years, thousands of sequences of HIV proteins have been collected, and we first developed a learning algorithm that was able to translate this data into knowledge of the prevalence landscape. By that I mean the probability of seeing a particular sequence in circulation. But what we really seek is the fitness landscape of the virus, that is the ability of the virus to replicate and propagate infection in vivo as a function of sequence with explicit account for the effect of coupling between mutations. So the prevalence of the virus is influenced both by its intrinsic fitness as well as how human immunity has pushed the virus around in sequence space. We seek the intrinsic fitness landscape because we then want to push and pull on it with a vaccine-induced immune response to corner the virus between being killed by the immune response or evolving suicidal mutations. So we then used approaches to study the evolutionary dynamics using approaches that, for example, Richard Feynman had developed in completely different contexts to deconvolute prevalence from fitness. We then tested that thus determined fitness landscape against in vitro experiments and human clinical data. And thus validated, we then went on to design an immunogen, or the active component of a T cell component of the vaccine, which is not made up of whole proteins of the virus as is typical, but only composed of parts of its proteome. These parts of the proteome are ones where it is very difficult to evolve mutations no matter what the sequence background, or what we call multidimensionally conserved regions. The issue is whether these parts of the proteome can be delivered into humans and animals in a way that leads to a big immune response, which can be protective. Recently, we have shown that using a platform that is the basis for the J&J and AstraZeneca COVID-19 vaccines, we can achieve this goal in monkeys, and we are now trying to move this concept forward with companies into humans using the mRNA platform. So now let me turn to the antibody arm of the problem. And upon natural infection or vaccination, antibodies are produced by a Darwinian evolutionary process called affinity maturation. I told you that if the receptor on the surface of a particular B cell can bind sufficiently strongly to the spike proteins, it gets activated. And then it can seed structures in your lymph nodes called germinal centers. Herein, the B cells start to multiply, but also mutations are introduced at a very high rate into the antigen binding region of this receptor. These mutated B cells then interact with the antigen, that is either the virus or whatever is in your vaccine. And if the B cell can bind sufficiently strongly to this antigen, it can eat it up. Without the details, B cells with a receptor that can bind more strongly to the antigen stochastically can eat more antigen and stochastically have a higher chance of receiving a survival signal. The other B cells die. A small fraction of these positively selected B cells are let out as memory cells and plasma cells which secrete this receptor in soluble form, and that is what is an antibody, but the vast majority are recycled for further rounds of mutation and selection. So you can see, as time ensues after infection, the affinity of the antibodies for the antigen increases. Now, here is a depiction of the viral spike of HIV. It has some conserved regions, shown here in yellow, but they are surrounded by highly variable regions shown in red and protected by these sugars shown in blue. The flu also has some conserved regions here, but it also has a conserved region in the stem of the spike. And these regions, the conserved regions, are necessary for the virus to propagate infection by binding to human cells, so they don't mutate as much. Now, recently, immunologists have found antibodies from patients that can neutralize diverse strains of these HIV or flu. They are called broadly neutralizing antibodies, or BNAbs, and they can bind to these conserved regions. BNAbs, however, usually emerge several years after infection and in small numbers for HIV, and rarely after influenza infection. However, their existence shows that the human immune system can evolve such antibodies and suggests the tantalizing possibility that properly designed vaccination protocols can lead to their emergence in high numbers in diverse people. That is, they can become the dominant response. So that's the question. Can we manipulate this affinity maturation process in a way that allows the subdominant response, that is broadly neutralizing antibodies, and make them the dominant response? The way to do that is that we have to immunize with variant antigens that share the conserved regions but have different variable parts. And so it is hoped that this Darwinian evolutionary process can then learn how to focus on the conserved parts. That's how an immunologist would say it. I want to change the immunodominant hierarchy. An engineer or a physical scientist would say, look, this is a stochastic, dynamic process, and the evolutionary trajectories that lead to BNAbs are very rare. Can I immunize to provide the right selection forces here such that these rare evolutionary trajectories become more likely? And we have pursued many directions in this regard, and these have included with many junior scientists and senior scientists, and these have included very basic studies, but have also culminated in understanding, or at least beginning to understand with Daniel Lingwood's lab, how to get broadly neutralizing antibodies that focus down on these conserved parts in the stem. We do a number of other things that focus on the antibody response, but including the trillion-dollar question, I guess, of what determines the durability and the memory of an immune response. But for today, I hope I have given you some snippets and an overview of at least some aspects of our work that focus on developing better vaccination strategies for highly mutable pathogens by bringing together approaches from engineering, physics, biology, and medicine. Thank you very much for your attention.
Thank you, Professor Arup. I invite Professor Vishwanathan Shankar, Professor, Department of Chemical Engineering, Indian Institute of Technology, Kanpur.
Good morning, everyone. My name is V. Shankar from the Department of Chemical Engineering, IIT Kanpur. And at the outset, I would like to thank the Academy for this opportunity to present my research in the annual meeting. The topic of my presentation is role of fluid and wall elasticity on the onset of turbulence in pipe and channel flows. Let me first acknowledge my collaborators. This work is done with Professor Ganesh Subramanian at Jawaharlal Nehru Center at Bangalore, and some of the experimental work that I carry out is done with Professor Devpam Das of IIT Kanpur. The PhD students who took part in the work from IIT Kanpur are Indresh Chaudhary, Ram Karan Patne, Muhammad Khalid, Bidan Chandra, Shailendra Yadav, and Shraddha Mandloy. The PhD student from Jawaharlal Nehru Center is Piyush Garg from Professor Ganesh Subramanian's group. It is very appropriate to begin the talk with the famous Osborne-Reynolds experiments on pipe flow. It is well known that Reynolds first carried out experiments in flow of water through a glass pipe and showed that fluid flow can exist in two qualitatively different regimes, namely laminar regime where the flow is very orderly and the turbulent regime where the flow is apparently chaotic. Now, even from the time of Reynolds, it was evident that the transition in pipe flow is very different in the sense that there is no fixed Reynolds number at which the transition occurs. In fact, the Reynolds number at which the transition occurs, while it is typically around 2000, it could be postponed even up to 10 to the 5. Now, the transition was marked by an abrupt appearance of localized turbulent structures called puffs and slugs, and a similar transition also occurs for Newtonian flow through rectangular channels, and this happens at a Reynolds number of around 1000. And there are macroscopic signatures of the transition in terms of the friction factor Reynolds number charts, wherein the friction factor deviates very sharply from the laminar value around the transition Reynolds number. Now, ever since the experiments of Reynolds, there have been a lot of efforts in engineering fluid mechanics to predict the transition from first principles using the Navier-Stokes equations. And this has turned out to be a rather very tough challenge because Newtonian pipe flow is stable to small perturbations at all Reynolds numbers. So this also is consistent with the earlier observation that I mentioned, that the transition could be postponed to very, very high Reynolds numbers if sufficient care is taken. A similar instability analysis suggests that channel flow is unstable at a Reynolds number of around 5800, but this theoretical prediction is much, much higher than the observed Reynolds number, observed transition Reynolds number of around 1000. So it is now understood that the transition is dominated by nonlinear processes, and in the last 20 to 25 years, there has been a lot of development in fluid mechanics literature on how there are new non-trivial unstable solutions called exact coherent states that emerge with increasing RE, Reynolds number, that dominate the transition. Now, in this context, there was an important paper in 2013 from Björn Hoff's group in Austria. They carried out experiments in the flow of polymer solutions and reported a new type of turbulent state called elasto-inertial turbulence. Essentially, these authors carried out experiments in flow of polyacrylate solutions of very high molecular weight and over a range of concentrations. And in their experiments, two types of protocols were followed. One in which the transition was forced by the injection of fluid, and other in which there was no forcing. And they observed the Reynolds number at which turbulence occurs as a function of polymer concentration. Now, the forced transition occurs in the Newtonian case at a Reynolds number of around 2000 in their experimental setup, while the natural transition happens at around 8000. Upon addition of polymer, while the natural transition is occurs at a much lower Reynolds numbers than the Newtonian value, the forced transition is stabilized, but beyond a threshold concentration, polymer concentration, the transition occurs at the same Reynolds number, indicating that the transition is independent of the forcing, and this is a hallmark of linear instability. Now, a similar transition was also observed by Srinivas and Kumaran for rectangular channels at Reynolds numbers around 300 to 350. So, these experimental observations suggested to us that there could be a universal linear route to elastoinertial turbulence in both viscoelastic pipe and channel flows. In a slightly different area of research, we also carry out research to understand how transition occurs in flow through deformable tubes and channels of the type that occur in biological flows. Here I am showing a schematic of an artery, flow in an artery, which has soft walls due to the tissues, and our research here tries to understand how instabilities occur in fluid flow through deformable tubes and channels. Now, here again I am showing an experiment wherein from Professor Kumaran's group, where we show that where they showed that flow in a PDMS tube of soft elastic modulus of the order of 17 kilopascals could become unstable at a Reynolds number of around 1000, in contrast to the rigid tube value of around 2000. The friction factor Reynolds chart also shows that the friction factor deviates from the laminar value at Reynolds numbers much lower than the Newtonian threshold. So, the key idea here in flow through deformable tubes is that there are new modes of instability that are induced due to the deformable nature of the solid wall, and our research, the research carried out in our group in the last 5 or 7 years has shown the importance of rheological constitutive modeling of the deformable solid in accurately predicting the transition in flow through deformable tubes, and we have developed a consistent Eulerian and Lagrangian formulation of the coupled fluid solid problem to accurately predict flow stability. Thus, in contrast to Newtonian flow through rigid pipes, when you consider either flow of viscoelastic polymer solutions or flow of Newtonian fluids through an elastic soft wall, both fluid and wall elasticities render the pipe flow linearly unstable. This is one of the main takeaways that I would like to convey through this talk, that either fluid or wall elasticity can make the pipe flow linearly unstable, and this prediction allows for a simpler transition scenario compared to the Newtonian pipe flow case, wherein I just mentioned that the transition occurs via the appearance of nonlinear structures called exact coherent states. The possibilities of supercritically stable states in the vicinity of the transition is quite analogous to Taylor-Couette flow and Rayleigh-Bénard convection in fluid mechanics. Now, here I show sample results from our research. Here I am showing the Reynolds number versus wave number plot at which for flow of polymer solution in a pipe, and the minimum of this will give you the Reynolds number at which the flow becomes unstable in experiments, and all these curves collapse when you suitably replot them. Here E is a measure of elasticity. E is called the elasticity number, and E equal to 0 corresponds to Newtonian flows. So, all the different neutral curves, they all collapse onto the same curve, and here we give a theoretical scaling for how the transition Reynolds number scales with the elasticity number and how the critical wave number scales with the elasticity number. Here are some comparison with experimental results from our group, and the red dots are experiments and the blue curve is a theoretical prediction. This shows that the experiments also show instability in the elasticity number range, where theory also predicts. Here is a more recent experimental observation from Bjorn Hoff's group again, and herein they show that there is very good agreement between our theoretical predictions, which are shown in these blue and red curves, and the black dots are experimental observations. The theory agrees well with experiments at low elasticity numbers, but at higher elasticity numbers, theory does not predict instability, but the flow nevertheless becomes unstable in experiments, suggesting that in this elasticity regime, the flow becomes unstable due to a subcritical mechanism. The authors also compared the prediction from our linear stability analysis, which is shown in this bottom panel, with experimental observations. And this shows that the experimentally observed structures are quite close to the predictions from a linear stability theory. Again, in drastic departure from Newtonian 5 flow, where the linear stability theory fails miserably. And there are very interesting future directions in which one can take this discovery forward. For example, in Newtonian shear flows, the turbulent state is disconnected from the laminar state, whereas we have shown that in viscoelastic flows, there is a continuous pathway from the laminar state to the turbulent state. And this could have major implications in understanding the so-called maximum drag reduction regime. And the key question that can form important area of future research is, can the linear instability that we discovered evolve directly to the MDR state? And there has already been some developments in this regard, wherein researchers from Cambridge have used the linear eigenfunctions from our study to continue the solutions to nonlinear coherent structures. And there are interesting takeaways even in the limit of very small Reynolds numbers, where there are instabilities in flow of polymer solutions. In the context of flow-past deformable solids, our research has focused on the development of a consistent formulation for understanding stability of fluid flows. In soft deformable solids, the strain, when there is a flow past a deformable solid, the strain in the base state is not very small, so one has to account for finite deformations. And we use the simplest non-trivial model that accounts for it, namely the Neo-Hookean solid in continuum mechanics. And if you do this analysis for plane coed flow, both linear elastic solid and Neo-Hookean solid yields qualitatively similar results. But when we carried out for pi-Poiseuille flow, the linear elastic model predicts an instability, whereas the Neo-Hookean model doesn't. So this points to the need of a consistent and independent formulation to resolve this. So we developed a consistent Eulerian Lagrangian formulation, and we showed that there is indeed no instability for flow in a deformable tube in the limit of low Reynolds numbers if you use the Neo-Hookean model. But if you use the Mooney-Rivlin model, that may show an instability. So this suggests that the flow stability is highly sensitive to the constitutive nature of the solid, especially at low Reynolds numbers. Some of these discrepancies also continue to higher Reynolds numbers. So our work suggests that one has to precisely characterize the nonlinear rheology of the solid while comparing theory and experiments. And unlike rigid solid surfaces, where plane coed and tube flows exhibit qualitative similarities in linear stability, here there is no such similarity, because there are drastic differences between stability of flow past, coed flow past a Neo-Hookean solid surface and flow through a deformable Neo-Hookean tube. So with this, I would like to end my brief presentation, and I thank you for your kind attention.
Thank you, Professor Shankar. I invite Professor Ravindra D. Goody, Professor, Chemical Engineering Department, IIT Bombay.
Namaskar. It's my proud privilege to present my research to the distinguished fellows of the INAE. My name is Ravindra D. Goody. I'm a professor of chemical engineering, and currently I also head the research park, the IIT Bombay Research Park Initiative. Let me just begin by giving you a quick background about myself. I'm a proud alumnus of IIT Bombay, BTech in 85, and then MTech in 87. And then I moved to the University of Alberta to do my PhD. I completed this in 1995. I've been a faculty of chemical engineering since 1995. In terms of research highlights, I'd like to say that my broad areas of research have been in process systems engineering, which essentially implies use of modeling, optimization, advanced control, and decision support systems for running our chemical plants, chemical processes better. I also looked at a number of applications associated with green engineering, carbon dioxide valorization, and various emerging problems related to energy and water. I have been guiding 21 PhD students. It's again a very proud feeling for me that 11 of these students have been placed in academia in various IITs, NITs, and private engineering colleges. I had a total of 82 journal publications, 75 conference publications, 6 book chapters with an H index of 26. Also translated some of my research into practice. 9 US patents have been granted, a couple of them licensed, 3 national patents that have been filed. I've been interacting quite a lot with the industry, as well as doing fundamental research, sponsored research projects 7 and consultancy projects with various industries in chemical engineering 16. Also conducted a lot of continuing education program courses. In terms of service to the community, I have been recently elected to the Executive Council of the International Federation of Automatic Control and also the Indian Institute of Chemical Engineers. I have also been the president of the Automatic Control and Dynamic Optimization Society of India. Thankful that I've been elected the fellow just recently and also been a fellow of the Indian Institute of Chemical Engineers. I would like to just summarize my research through just one slide, which essentially is an example of where my research has been applicable. This is typically an example of an energy translation. The fuel, there is a lot of energy that's locked into the fuel. You want to maximize the energy transfer for power applications. So you essentially want to focus at high efficiency combustion. Now to enable this, there are several aspects that need to look into. The first is, of course, sensors. Where do you locate the sensors? What type of sensors that you choose and deploy? So in a typical combustion application, you have the diversity of sensors, be it fuel quality, which is infrequent. You have acoustic sensors that give you information about the flame when it burns. You have thermal sensors that sense the ambience around the flame. You have flame images, high-speed cameras that essentially measure the health of the flame. And you also have emission information in terms of what gets emitted, the gases, the unburned fuel, the temperature, and the light. Now, typically, if this is the kind of sensors that you choose, it can be generalized to any other application as well, that there could be a diversity of sensors. How do you bring this information together to make sense of how good your combustion is? And that's what goes into a block which is illustrated here as the combustion quality assessment. In this case, what happens is we have basically a benchmark, maybe past seen performance of how the performance has been. And you compare the current performance with the past best known performance and assess the quality in terms relative to that benchmark. But now comes the important aspects of the research. How do you know that that benchmark is really the best? There is nothing sacrosanct about the benchmark, and therefore you need to start building a combustion system model that essentially gives you a theoretical limit as to how best your combustion efficiencies can be. Now, it's not good enough to just stop there. What you need to do is you need to use all of this data to basically tune the combustion model and then make it what's now called in industry parlance as a digital twin. And now you use this digital twin to, along with powerful optimization algorithms, to find that peak point where your combustion efficiency is maximum. So this combustion system model, a digital twin, along with advanced optimization and control tools, will essentially generate targets for how do you want to run this combustion, and the advanced control aspects will essentially implement those targets through local regulators or feedback control, and that promotes high efficiency combustion. So essentially it involves sensing systems, modeling systems, advanced optimization systems, control systems. I also mentioned about fault detection and diagnosis in my research. Now, fault is one example of a very severe degradation. However, even the health of the combustion in terms of being able to go from very high efficiency to a medium efficiency is some kind of a deterioration. You would like to quantify that deterioration and look at what has caused, what are the bad actors that have caused the deterioration, so that you can alleviate those problems and push the efficiencies as close to the best known combustion as possible. So that's what fault detection and diagnosis is about. Performance assessment and quality improvement is all about. So all of these aspects of systems engineering, namely modeling, optimization, control, advanced decision support systems, fault detection and diagnosis, these have been the thrust of my research areas over the last several years. However, coming to more closer aspects of my research, I would like to highlight some of my research in the area of artificial intelligence and machine learning. Now, traditional approaches have focused on this aspect of artificial intelligence and machine learning by treating them as data-based approaches where you have a lot of data coming in and you want to make sense of this. One of the key differentiators that my research has brought in is to bring in first principles of physics into the AI and ML based approaches. The reason being that most of these AI and ML approaches are known to be not easily interpretable, not easily explainable, and not easily extrapolable. And so to be able to enhance the accuracy of these AI and ML models on all of these aspects, what we have sought to do is bring in physics-based knowledge in the knowledge representation aspect of AI and ML. And through this, what we seek to do is make a modest contribution to recoin AI, which is typically known as artificial intelligence. We'd like to recoin this as augmented intelligence. In terms of contributions, what we have done is we have basically done physics augmented AI and ML in various applications like aerosol science and engineering. They're really tough systems to understand. There's a lot of complexity and uncertainty with those. Even if you try to model them, we try to see how physics augmented AI and ML can help solve those problems. We also looked at various other applications related to pharma. Also looked at the energy sector in this area. Industrial applications, a lot of these have been seen in companies like Aditya Birla, Yokogawa, Linde, Praxair, Reliance, and at Honeywell. Also given a lot of pedagogical outreach talks through continuing education programs, industrial webinars, and invited talks. Let me just dwell into some of my sponsored and consultancy projects. I'm just choosing this AI and ML because this is what I've been doing during the last 5 years. One of my research has essentially focused on engine performance monitoring and integrity analysis. This is a highly safety critical application where we have used AI and ML approaches to be able to solve some of those or assess the engine performance. We also currently been involved in a very interesting project associated with water quality and management. Basically, this is called Lotus or low cost innovative technology for water quality monitoring and water resources management. And this is something that we have engaged with European Union. This is a project between India and EU under a water cooperation program. And we are trying to look at several use case scenarios, drinking water, agricultural water, wastewater and the like, and trying to see how best we can deploy sensing systems, optimization, and advanced control systems to ensure water quality as well as water availability in various rural and urban areas. In terms of consultancy project, this is a quick glance of the nature of the projects that I have done during the last 5 years, looking at minimizing quality in carbon black, advanced intelligence for demand forecasting using AI and ML, AI and ML based predictive model for alumina calciners, demand forecasting using AI and ML, soft sensors for high performance integrity of locomotive engines, progressive cavity pump failure analysis in large coal bed methane fields, and closed loop model refinement. Just a quick glance of some patents and publications in this area. There are a couple of patents that we have filed. This is in the batch and pharma area. This is in the disinfectant dosing in water distribution networks. Also in water, vehicle-based water distribution. So this is has to do with quality of water, and this has to do with managing the distribution of the water. So in this particular area of AI and ML, we have generated in the last 5 years about 39 publications. And in terms of PhD guidance, a couple of my PhD students won the IITB Excellence in PhD Thesis Award, one in the area of enterprise-wide optimization, the other in the area of advanced decision systems for water quality management. And I'm currently working with the Prime Minister Research Fellow in the area of physics-inspired approaches in AI and ML. This is an ongoing project. In terms of outreach, I've essentially delivered several lectures. One is the Acharya P.C. Ray invited lecture just last year on exciting opportunities in AI and ML for the industry. Industry platform talks to several public sector undertakings in the oil and gas. We looked at digitalization and AI and ML opportunities. Several academic institutions have also invited me to deliver talks in this AI and ML area, in addition to a lot of continuing education programs with several industries diverse. In terms of administrative positions, I've been a professor in charge currently with the IIT Bombay Research Park. So I did the chemical engineering department for 3 years prior to that, and also have looked at continuing education and quality improvement program 2015 to 2017, where I also donned the role of a principal coordinator appointed by AICTE to look at aspects related to various QIP centers, major and minor. At the national level, I've held several positions. I've been executive council member of the Indian Institute of Chemical Engineering, DST, PAC member at the DST, sir, president of Advanced Control and Dynamic Optimization Society. RUSA, I've been a member of the Evaluation Committee, and Ruchita Avishkar Yojana, also a member of the apex body. In terms of the international appointments, I've been elected to the Executive Council of IFAC. I've been international reviewer for strategic project grants at NSF and INSERC Canada, as well as National Qatar Research Foundation. I've been an associate editor of IFAC, International Federation of Automatic Control, Journal of Process Control for the last 11 years, and also Frontiers in Control Engineering. One of the other interesting assignments was during my lien at Honeywell. I also was the editor-in-chief. I was the founding editor-in-chief of the Honeywell's technical journal, which we call as Exponent. Established a board of editors constituting of various corporate fellows in Honeywell, and it's still running over the last 10 years as a very successful internal journal, technical journal. In terms of services of the committee, AIML area, we recently started a new Center for Machine Intelligence and Data Sciences at IIT Bombay, where we established minor and IDDP programs, as well as initiated Senate approvals for the MS and PhD programs. I would just like to give you a quick glimpse of one other activity, inter-university, international activity in terms of basically human-centric AI. This is really a consortium of 7+ universities internationally, all of these, where the focus has been on how to have AI tailored to humans rather than humans learning AI. And that's something, very interesting exercise that we have jointly been working on in this area. I'll just wind up my talk with a couple of quick initiatives. I talked about the Lotus project, which we have been doing with IITG on the IITB on the Indian side, and a bunch of people on the European Union side with these as use case scenarios. I also looked at predictive analytics for carbon black in Aditya Birla, and also for the process industry in a crude distillation unit with Yokogawa. Let me just wind my presentation again with a quick note of gratitude and thanks to the INAE for inducting me as a fellow. I really look forward to all the very exciting interactions that I propose to carry out with the scientists and engineers at the INAE. Thank you very much. Namaskar.
Thank you, Professor Ravindra. I invite Dr. Amol Arvind Rao Kulkarni, Scientist, Chemical Engineering and Process Development Department, CSIR, National Chemical Laboratory, Pune.
Hello everybody, I am Dr. Amol Kulkarni. First of all, I thank INAE for inducting me as a fellow from this year. I'm going to give a talk on the work that we do in my group. I'm going to give a talk primarily on the design of novel flow reactors for continuous manufacturing. So why continuous? Primarily because it's efficient. If you look at some of the natural examples around, our brain works continuously, our thinking, sensing, all happens continuously. During the daytime, the photosynthesis happens continuously. When we want to travel from one end of the city to the other end, that also happens continuously if there are no signals, no speed breakers, and that is what we like. Fortunately, our kidney works continuously, and our growth or aging also happens continuously. All these things, we feel them efficient because these are all natural and they are all continuous. But continuous is not very new to us. Continuous manufacturing at large scale has been happening for a variety of things. You take all the cookies or the biscuits that we eat, or even the breads that are consumed by many of us on day-to-day basis. Assembly line of the car operates in the continuous mode. Pharmaceuticals, the tablets, capsules, the formulation happens in continuous mode. Even nowadays, the recipes and the idli, dosa, all are also manufactured in continuous mode. Now, primarily because it offers very important advantage, that is consistency in the quality at any point of time. That is the case, why not to implement that in the chemistry? But implementing continuous manufacturing in chemistry is not very new too. Most of the bulk chemicals are being manufactured in continuous mode for several decades. But then what is new? The new thing is that applying continuous flow synthesis at the lab scale for complex reactions, which are typically used for manufacturing or synthesizing APIs, dyes, perfumery chemicals, agrochemicals, and so on. To give you a brief history of where all it started. So basically the making chemistry in flow started almost 20 years ago, where most of the chemistry community, which was using the round bottom flasks and the conventional batch reactors for doing the synthesis, they started operating the synthesis in continuous mode. And a large number of chemistries were demonstrated in small scale at the lab scale in continuous mode. They are typically exothermic reactions, endothermic reactions at high temperatures, reactions involving unstable species which are typically not possible to be done in batch mode, photochemical reactions, electrochemical reactions, plasma-based reactions, and so on. Once these are done, and when the chemistry community got convinced that there is a merit in doing the things in flow, then they realized that while the synthesis happens in flow, the workup or the purification was still in batch mode, and that takes much longer time than the reaction time. So then the automated synthesis platforms came into picture, where many integrated systems, including the inline process analysis, inline separation, also were implemented. And when all these things were happening, it was also realized that while the advantages of miniaturization, advantages of small systems can be realized in the labs, they can definitely be taken to the pilot scale or to the commercial scale. And that is where the chemical engineers stepped in, and microreactors of variety of designs, tubular reactors, pinch tubes, various flow reactors, all came into picture, and they were being evaluated for variety of chemistries which were not done earlier. And eventually, they all came into practice in terms of continuous flow manufacturing, where single-step, multi-step reactions were implemented at large scale. Now, when you go from the small scale, single system, single microchannel or millimeter scale channel, or a straight tube of say 1 by 1 millimeter diameter or 2 diameter, and taking it to a large scale, it has several challenges. So typically, when a system operates and when you see that the fluid enters into a tube from one end, the tubes are typically straight tubes. They're typically very long in terms of aspect ratio, and it helps in two ways. Smaller the diameter of the tube, higher is the heat transfer area per unit volume. For a tube of 1 millimeter diameter, your heat transfer area per unit volume is 4,000 meters square per meter cube. At the same time, if you are using 1 meter diameter reactor, then your heat transfer area is only 4 meters square per meter. Smaller tubes also offers very small diffusion lengths that facilitate rapid mixing. And so to take these small tubes at the large scale and also increase the number rather than increasing the size was essential. But you can't use straight tubes. You must need to have some modification being done. So people started using helical coils, the tubes in the spiral form, and so on. But then with very large aspect ratio, there is a very significant disadvantage. And the disadvantage is mainly the axial dispersion, which means that when the fluids flow through the tubes, the walls of the tubes have zero velocity. And so the fluid segments, elements near the wall have zero velocity, while the fluid element at the center of the tube is moving at 2 times the superficial velocity of the fluid. When this happens, along the length of the reactor, or the tube, you always see that there is a velocity gradient along the radius, and because of which any tracer which enters into the system after a certain distance start getting spread over the entire tube, and so that is what is called as axial dispersion. Now, this is very detrimental if you are having the reactions where there are sequential reactions are possible, which means that if you are doing the chlorination of acetic acid, it gives you monochloroacetic acid. It also gives you dichloroacetic acid if monochloroacetic acid remains in contact with chlorine for longer time. And it can even go to trichloroacetic acid. Now, such things can be avoided only if your reactants move together simultaneously without getting diffused or dispersed in the entire system. And so the reduction in the extent of dispersion is essential to avoid the formation of side products in all such reactions. Here I'm going to give you two examples of two different novel reactors that we developed in my group. The first is called pinch tube. Pinching of straight tubes happens very easily. What you have is by pinching from two sides, you get a depth. The pitch between the successive pinches can be one design parameter, and the angle between the successive pinches is the second design parameter. And pinching reduces the reactor volume by around 6 to 8% without reducing the heat transfer area, which is very significant kind of value in terms of the design of or usefulness of a simple tube as a flow reactor. Now it has the potential to be used as high throughput flow reactor because small reduction in the areas also helps in locally increasing the pressure gradient and also ensuring that if it is a two-phase flow, it basically gets pinches at the point of pinching and you get fine dispersions beyond the pinch points. And you just don't need to have one pinch point, you can have a sequence of pinch points. So what we did was that we evaluated the efficacy of this design. Initially in a glass tube, we made a pinch tube of the glass and we studied it at different flow rates for mixing of two fluids. And what you can see here is that in a small tube of say around 4 millimeter diameter, when we pinch it and at different flow rates, right from 10 ml per minute to 60 ml per minute, you can clearly see that even at 30 ml per minute, at the fourth pinch, at the fifth pinch, the mixing was complete, which was not possible at low flow rates or which was not possible even at earlier pinches. And for the case of straight tubes, it will take really long time and long distance. Second advantage is that the pinch tubes can be put in any shape and form that you want. So we initially made the helical coils of the pinch tubes, tested in the labs. Then we have transferred this, licensed this design to a company from Mumbai, where we have now been able to go for really large scale pinch tube reactors, which you can see here is a 12 liter volume reactor, and this is 165 volume liter reactor. It is being used for very high throughput reactions. Such reactor is a flow reactor without moving components for handling solids. Now, in general, it is known that if the solids are getting formed in the reactions, you need to have something to push the solids out. In the flow reactor, there is a major disadvantage because in the tubes, if you are having, or even in the pinch tubes or any system, if the byproduct or the product from the reaction is solid, it is always possible that it will clog the channel. Now, as a result of which, you really can't use small reactors or micro reactors for handling the reactions involving solids. So we came out with a new design when we systematically did the CFD simulations of the concept that we had proposed, wherein the reactants enter from the top, and then there is a series of cavities which the dimensions of which are optimized using CFD, and also there are angles at which specific the exits ports are kept for between the two at the end of every cavity. And we optimize these designs. We did a detailed CFD simulation. We studied the hydrodynamics of this, including the mass transfer, including the heat transfer, and the residence time distribution. We could see that even for such a simple system, we were able to handle almost glass particles, magnesium hydroxide, activated carbon, starch. And we also carried out the reactions involving beta-naphthol for synthesizing specific and naphthalene for synthesis of specific organic compounds which precipitate easily. And we were able to handle 22% of slurry without clogging for a long time. So this is a very, very important thing when it comes to handling solids in continuous flow reactors without having any moving components in the system. As a chemical engineer, when we look at all these kind of reactions and where we want to use the reactors for carrying out reactions and show how they work, we typically tend to classify them in a relatively simpler manner. Because although the chemical reactions are classified based on their nucleophilicity, their aromaticity, the substitution that happens, etc. But for us, it becomes important to monitor the reactions in terms of rate of reaction rather than what is getting formed and how it is getting formed. So rate becomes more important. So the best way to classify these reactions is, as I have shown here, like very exothermic reactions, shock sensitive reactions, multi-phase reactions which are mass transfer limited and so on. So we have a few set of questions that we typically ask when we do any reactions, and where collaborations with the organic chemist is a must. So we try to classify the reactions in terms of their kinetics, whether they are fast or slow reactions, are they exothermic reactions or endothermic reactions. We classify them in terms of their thermodynamics, then also number of phases involved, the reactants, products, the stability of the individual components, reactivity, and so on and so forth. And then we ask the question, why we should make them continuous? And if answer to any of the above points is yes, that is meeting certain requirements, we must move into continuous. I'm going to show you two case studies here. The first is of a drug, it's Ivacaftor, world's most expensive drug, which is used for cystic fibrosis, treating cystic fibrosis. It is done in collaboration with one of my organic chemistry colleagues, Dr. D.S. Reddy. And where the key step was an ozonolysis. In general, when you do the ozonolysis in batch mode, you have to do it at minus 78 degrees centigrade in the presence of large quantities of solvents. Here we made them all in continuous mode at minus 10 degrees centigrade. In the reaction time was 1 second. Subsequently, we kind of made the arrangements to kind of remove the excess ozone as well as the oxygen, which goes to a scrubber. And the product, along with any ozonides in that, quenched ozonides, it goes to the subsequent next reaction. And depending on the reaction kinetics, we could optimize the reactor sizes, reactor volumes, as well as the conditions to get the maximum yield from each step. And we could put up a continuous facility for synthesis of this drug. And we were able to make almost 10 grams every day, which meets the requirement of treating almost close to 5,000 patients every day. Second such example is when you go for, again, using this continuous flow synthesis. It's a simple example. When you want to put a hydroxyl group on any aromatic ring, you need to follow typically 4-step protocol. The first is you do the aromatic nitration, then hydrogenation, then diazotization followed by hydrolysis. So we took the case of cumene and we carried out the nitration with fuming nitric acid. We carried out 65 experiments in 1 week using a simple system, including the nitration, quenching, liquid-liquid extraction. Then it goes to the next step of hydrogenation at high pressure at 100 degrees centigrade at 40 bar in a HQ system. Then we carried out the diazotization at 5 degrees centigrade in a really short time, almost 2 minutes. And then the diazonium salt which gets generated is sent for hydrolysis at high temperature in a microwave with sulfuric acid, where it happens in more than close to 5 minutes. So you can look at the time required for completing all this work, and the total synthesis time was reduced from 21 hours, it is required in the batch mode, to 20 minutes in the continuous mode. This is the advantage of moving from batch to continuous using these miniaturized systems or microreactors. In the recent time, we are also working on developing continuous mechanochemical systems. What it means is that in most of the times when we do a synthesis, a lot of solvents are used for carrying out reactions. Now here, instead of using the solvents, we carry out almost solvent-free reactions, where the solid substrates react with each other in a extruder kind of a thing system, a screw, and we control the dosing rates of the reactants. If one of the reactants is liquid, then we use a pump. The other reactant is dosed in the form of using another screw system. We maintain the temperature in the reactor using a jacket and carry out variety of reactions. Recently, we carried out 12 different types of reactions using the same system. You can look at the reaction time. So typically, the reactions which need several hours are now pushed to almost 20 seconds, 30 seconds as the reaction time to get completed with a very high yield. So this is one area which is very, very important, because on an average, we as a country import 65% of the solvent that we use. So if we are able to reduce that solvent quantity even by 10%, 20%, it will be a significant import substitution. And it will also make our processes more and more efficient with smaller footprints. The last case I'm going to cover, it's a continuous process for silver nanowires. We started this work almost 4.5 years ago, where we started looking at, can we make these expensive materials in flow? Because these all have very significant, many advantages, like solar cells, displays, sensors, printed circuit boards, magnetic devices, flexible electronics, and so on. And the overall turnover of these materials is going to increase significantly over next decade. So considering the flexible electronics around, we thought that we should enter into this domain. A typical batch protocol needs silver nitrate in ethylene glycol. We add PVP as a capping agent, and you need a halogenated salt as a etching agent, which facilitates the growth in one direction. Temperatures are always above 120 degrees centigrade. And typical batch reaction for few milligram scale needs around 180 minutes. We understood the reaction kinetics, reaction mechanism. The reaction starts when the solution is pale yellow and it moves towards a silky grayish color at the end. And depending on the operating condition that you keep, you can produce kind of rods or a mixture of particles and wires or only wires. A few parameters become important, that is temperature, initial concentration, concentration of halogenated salt, etc. And all of these have to be controlled to make sure that what you want. Now, what do we want? We want a complete conversion of the limiting substrate, that is silver nitrate. It's an expensive material. Second thing is that we want to control a narrow distribution of nanowire diameter. We should have a sufficiently large aspect ratio. We should have excellent mixing, local mixing, but overall it should act as a continuous flux flow reactor. It should be an isothermal operation to make sure that the reaction progresses everywhere in the same manner. There should be no or minimal deposition on the reactor wall, because any deposition is loss of the material. We checked almost we studied it in detail. We understood every parameter. We developed almost systems having 42 different types of reactors and finally optimized one. So recently we demonstrated that we have licensed this technology to a company now. We were able to make really large quantities of this material, and the value of the material is really very high. It ranges from $200 to $600 per gram, depending on the size that you make. We also had to check whether the material is useful. So we made formulations of inks and put them in the simple inkjet printer. We printed different patterns on the paper. We also checked whether those printed patterns are really conducting. And here you can clearly see that if I connect two ends of the printed pattern anywhere on the paper surface of the paper with a strip of LEDs, the LEDs glow, which indicates that the material is very, very useful. We have now taken it to pilot plant scale, and we also developed many other processes at the pilot scale. We start with the reaction kinetics. We do a systematic reaction engineering, identify the right devices or the reactors, study the transport phenomena in those reactors. Then we go for design, demonstration, optimization, and scale up. This is the entire cycle that we follow for every single system or the reaction. To summarize, continuous manufacturing is the most optimal way of exploring chemistry and easily translating into feasible process. Every chemistry needs different attention. Engineering challenges are there, and they have to be tackled by systematic approaches. Classical reaction engineering is important, that needs to be refined to make it relevant at all the scales. And high value, low volume chemicals and materials are the new areas of investment in the chemical industry, where we must move. Thank you very much again. Thanks a lot for inducting me in the INE. Thank you.
Thank you, Dr. Kulkarni. I invite Ms. Vartika Shukla, Chairman and Managing Director, Engineers India Limited, New Delhi.
It gives me great pleasure to share my views on looking at the changing energy landscape for the future. As we all know, the Honorable Prime Minister has targeted 5 key points towards our commitment as a nation in COP26, and one of which in 2070, the nation should be net zero. Global warming has always been an extremely important factor for all investments, all decision making, and in future as we go, looking at the journey of the energy sector, looking at energy as an integrated and composite of all various forms is how we have to steer the complete investments, the technology, the decision making process, both as corporates, as R&D, as teams and as organizations who want to sustain and flourish with a profitable growth. Specifically, when we look at the global hydrocarbon scenario, today we are seeing that oil is a very volatile commodity, and for a country like ours, which is 85% dependent on imports, it is a very crucial element in terms of the price and the inflation thereof, and the complete reliance on imports and not being self-reliance actually leads to a lot of stress on the Indian economy. And that is why, as we go along, all our efforts are to be made into areas which enhances our self-reliance and reduces the dependence on both oil and gas imports. Needless to say, to reduce the carbon footprint, gas in the future is considered to be a bridge fuel, which is looking at 7% to 15% gas mix in the primary energy. And all companies are channelizing their capital to rebuild and diversify into renewable beyond the natural gas. Clean products are the future, looking at capturing the carbon which is emitted in terms of carbon capture, and in the next step as utilization, looking at green hydrogen as a potential feed for various end uses, is how India is looking at the changing energy landscape. However, petrochemicals, which is almost 1/3 of the energy, which is 1/3, and petrochemicals, which are way low in per capita as per global consumption, is an area which is again garnering more and more investments. The world has transitioned into a very fast pace, right from the Kyoto Protocol in 1997 to the Paris Sustainable Development Goals in 2014, looking at now COP26, looking at electricity as a tool for transportation, for sustainable mobility, looking at green energy supplementing the need for EVs, looking at enhancing solar PV, where the costs of solar PV have really come down to just above 2 rupees per unit. These are all very rapid transformations, and looking at lowering of these renewable costs in future, as also the access of energy to all end users, which is targeted to reduce emissions, ultimately leading to welfare and growth. These are the objectives. Today, if we see the market, the consumer has a variety of energy types which they can choose, and therefore the decision making process for somebody who goes out to buy a car, whether they buy an EV or they look at CNG or they look at petrol or they look at diesel, these are all a variety of options which are available. So ultimately, as we go in the future, of course it is price driven, and it is very, very dependent on what the consumer is thinking, how these variety of options are looked at by the consumer, and then the demand creation occurs accordingly. Specifically, let me focus on how renewables are likely to change the world as we go in future. If we see in the current scenario, we have the share of electricity today on an average from renewables just about 20% or so on a global level. And as we move forward and we look at targets set by all the countries and investment made, it is likely to go almost 50% in 2050, which means that overall share of energy consumption, energy share in the power generation alone is more than 80-85% in 2050, which is really resulting out of majority of solar power additions and a significant addition in the wind energy. The solar and the wind are actually driving the rapid transformation and rapid inroads into the percentage of renewable in the total share of power. The storage aspect of energy, once it is the solution is found, a viable solution is found, this may even leapfrog to a much faster pace. Looking at fuels, now how do we get, where from do we get all this energy? Whether we look at oil, natural gas, coal, all these various sources of primary energy, as we look in future and meeting the goal, we have a transformation occurring right from 2030 onwards, which is at a significantly rapid pace. And the shrinkage of oil demand, if we were to believe the projections of IEA, look at other organizations who have forecasted the reduction in oil consumption. Starting today at about 100 million barrels per day, we are looking at a reduction down to 22 million barrels in 2050. And natural gas demand, natural gas being a bridge fuel towards a green economy, would peak at around 2030 and would again reduce significantly to a pre-2000 level to almost to in about 2050. Coal, which is going to transform not just to the power sector, but as we see forward, there could be a penetration of the coal gasification technologies, which look at poly generation and fulfill, at least for the developing country like ours, needs for polymers, petrochemicals, for fuels like methanol, which could be blended and sustain the growth which is required in petroleum, oil, liquid fuels. So total fossil fuel reduction on an overall basis as we move is likely to begin by 2030. Until that time, the oil and gas will sustain the majority share in the meeting the primary energy and diminish to more than 60% reduction by the year 2050. And this is from all the policies, all the declarations which have been made by various countries, including ours, in terms of looking at a net zero goal in the coming years. The crux to all this is the greenhouse gas emissions, and let me just focus on the carbon dioxide emissions, because that is what can be captured with the industry that I come from. In 2018, there was almost on a global level 34 gigatons of carbon dioxide emissions. And if we have to see these interventions which I just mentioned a while ago, it is likely that today the per capita CO2 generation or CO2 emissions of 4.4 tons could come down with the increase in per capita consumption of the developing nations to even almost 1/4 by 2050 were this transformation to happen. Of course, it is a function of the aspirations of the nations who are growing. It is also a function of the population growth that could plateau on a global level. In fact, I was reading just about a few days back that even in the case of India, it is likely that the prediction of the flattening of population could be even more rapid than what was predicted earlier. India's energy demand is expected to grow significantly to almost double in the next 10 years. India has committed a lot of investment into clean energy. India has also committed to increase its refining capacity, which is contrary but required to meet the transportation fuel demand. We also aspire, as I mentioned, to increase the gas mix in the primary energy to 15% by 2030, enhancing petrochemical growth, petrochemical end product use, clean fuel, energy efficiency, having more share of renewables, again laid out by the COP26 commitments, and looking at Make in India as a boost to manufacture and boost to increase the productivity as well as employment generation of the country. Very simply put, the net zero roadmap in the future rests on some of the important considerations, looking at energy efficiency, which is again reducing with technology innovation, intervention and better practices in operations, better operating procedures, reducing the energy consumption. Consumer behavior is extremely important. in awareness of best practices and how we do little things in our own day-to-day life, and also how industries adopt best practices to reduce their energy consumption and enhance their efficiency. Electrical mobility, which is a function of the cost, as well as a lot of other storage technologies which could play a very critical role. In times to come, the looking at CCUS, carbon capture utilization, is an area which is of immense importance, particularly to the R&D, and looking at how to integrate this to the existing industries. Renewables play a very important role in the net zero and well-to-wheel understanding of all these aspects is extremely important to get a carbon footprint. Finance is another factor which will play a very crucial role. How corporates look, how corporates are looked by institutions who are giving finance to put up these investments. Either these investments are going towards the conventional fossil fuel projects, or they are looking at projects which are integrated with green technologies. Green hydrogen, with the cabinet clearing the green hydrogen mission and allocation of funds to it, is a great step. It is something similar to the BS6 leapfrogging, where India leapfrogs from the fossil fuel regime to the green hydrogen regime. Biomass, almost close to 650 million metric tons, which is available in the nation. How to valorize it? There are several pathways to valorize the biomass. Specifically, I will just spend a few minutes into the green hydrogen. We have been talking in a very animated and very exciting manner into all colors of hydrogen, whether it is green, grey, turquoise, brown, blue, all of these. And while a majority of the hydrogen is consumed in the refinery and followed by the fertilizer sector, there is huge room for hydrogen to end up as fuel, huge room to end up as for other heating applications in complexes, and it is a feedstock for other sectors than the conventional oil and gas and the fertilizer sector. There is huge room for that to be also as transportation fuel. So there is a lot of fast track happenings in terms of the technology penetration into the market. And as we look in the future, the cost of green hydrogen, which is a present generation of ranging from 2.5 to 4.5 US dollars per kg, could be, which is significantly attributed to the OPEX, which is the cost of electricity. Looking at cost of electricity coming down in the near future, it may even go very rapidly on the cost curve and break through at a point where the electrolyzer costs are low, where the green energy, green power cost is low, and we have the breakthrough of the right technology of electrolysis for the production of green hydrogen. Biomass is another area which is found huge success in terms of valorization in the country. We already have second generation biomass plants coming up with various technologies in the country. EIL as a company is also moving very swiftly ahead in this area. We are implementing the first bamboo refinery of the world for ABRPL in Numaligarh, and also have very recently signed a collaboration agreement with Chempolis from Finland to look at valorization of biomass, not just for 2G ethanol but for other products. This is an important imperative which has been expedited. 20% ethanol blending, which was preponed now to 2025, and there will be several petrol pumps, as the Honorable Minister has announced, which will have 20% ethanol blended petrol available. Electrical mobility. This is one thing which is a big elephant in the room, has always been for the last 3 to 4 years. And there are several aspects to this in terms of not just looking at technology and manufacturing aspects. It is also looking at consumer behavior, the policy and the incentives which are provided, looking very deeply into material research, particularly into the chemistry of the battery technology and the sustainability and the longevity of the batteries in terms of mileage, efficiency as a result of that, the infrastructure in the nation wherein a lot of OMCs are now putting up a lot of charging stations, how quickly, how frequently, how closely each of them are available. And maybe in future, as we see, the primary target and a game changer for EV may not be four-wheelers, it could be, as we already see a lot of three-wheelers are on the conventional lead-acid batteries, and the two-wheelers who do city mileage could actually transform the sector to penetration of more EVs and even change the way the pattern of petroleum products or the consumption of petroleum products go in the future. We cannot close any discussion on energy without mentioning coal. Coal is the only reserve that India has. There is already impetus to gasify almost 100 million metric tons of domestic coal, which is important in terms of feed security, in terms of energy security. There is huge potential to look at syngas generated for a variety of reasons. One is of course CO2 sequestration, CO2 conversion, clean coal technologies, reducing the dependence on crude imports, and looking at several products which will add to our portfolio, not just in sustainable fuels, but also looking at petrochemicals as a whole. For doing this, INA has a great role to play in my view, because the organization, the leadership here, the illustrious members who are fellows and who are stalwarts in the industry have a holistic approach. So bringing this approach together from R&D and innovation to the industry is a very crucial role in my mind, which can actually look at bringing more tangible results, and it can have a very huge multiplier effect as well. So looking at laboratory level, new processes, new equipments, looking at centers of academic excellence, looking at specifically distributed approach, looking at local problems, also smoothing the energy entry barriers, which is a very crucial thing for a new technology to penetrate the market and get acceptance of somebody who's investing it. Looking at R&D lab partnership in a different manner, looking at maybe competitive research, which even the oil sector has done recently in some of the project, looking at competitive product development. I mean, it's a holistic approach which is extremely critical moving forward. We all do have problem definitions. We know where the problem lies, and there is a lot of innovation and a lot of thought process to generate idea, to brainstorm, and there is a value proposition, a solution proposition. And these three elements are together extremely relevant and probably sufficient to call and bring out innovation at all levels. And I would like to end by a quote by Thomas Alva Edison, that when he said, "Anything that won't sell, I don't want to invent." So coming from the industry and at ground level, seeing that something which is of value actually finds end use and finds investment, I hope to cherish that always, and work together with the INA fellows and my colleagues and my seniors there to bring this to realization and fulfill the obligations both as a chemical engineer, as an INA fellow, and to both my organization, industry, and the nation as well.
Thank you, Ms. Shukla. Ladies and gentlemen, thank you and Jai Hind.